Yeah, and I think the point of Larry's talk, I think Larry hit it home, is that there's a lot of infrastructure that has to take place to get the research off the ground that needs to happen to make these things possible. What Larry's talking about is really from a programmatic point of view. How do you actually start generating the funds needed to make real changes? Or else you're just doing things in a laboratory. Do you want me to wear the microphone?
Yeah.
Should I go through? The first thing, and this is going to be some of the how I think that you're discussing, the first thing I want to talk about is basic linearity and efficiency techniques for power amplifier design. And this is stuff that has been around for a while, but some people in the radar community may not be familiar with basic techniques to design amplifiers for higher linearity and efficiency. And so what I'm going to do here is I'm going to start from this, and I'm going to try to walk us down the road from basic linearity and efficiency techniques to real-time reconfigurable and adaptive amplifiers and waveforms. So that's what we're going to do for the rest of this tutorial. And Bob's part will be to discuss a lot of the waveform side of things that we're trying to merge with the amplifier. So I'm going to talk about basic amplifier theory and move on from there to some of the innovations that we've tried to put together with that. So linearity versus efficiency. What are these two things and how do they affect power amplifiers, particularly in radar? Efficiency obviously reduces power consumption. We'll talk about some metrics for this. It also requires operating the amplifier in compression, as we showed earlier at the very beginning. Linearity is related to spectral constraints. Poor linearity means it will have spectral spread. And to get linearity, we want to back the amplifier off from compression. We want to operate in very small signals. So we have a trade-off, a tension here. And the question is which one wins? And how do we try to get them both at the same time? Or can we? So spectral constraints are given by masks, as I mentioned earlier, and these masks are given in the RSEC in the United States, which is the Radar Spectrum Engineering Criteria, and they're implemented by the NTIA. Now, how does linearity actually cause spectral spreading? This is something that puzzled me for a while. What's interesting is when Larry talked to me in 2007, I was getting into this area. I was a very young new faculty member. I was trying to learn things. And so I always go back to the basics, and a lot of times at conferences you hear terms thrown around and you don't understand how to connect the dots. And this is one of the things I was puzzled. Well, how does nonlinearity cause spectral spreading? So we can actually understand this if we take a simple nonlinear system. Now we know that if we have a nonlinear system, we can approximate, if we have enough terms in a polynomial, we can approximate it by a polynomial series. So let's just assume we have a simple nonlinearity that has 3 as a third order nonlinearity approximation. So the first two terms here would be the linear terms, or the affine terms. And then we have a squared and a third. If we put in two tones, let's just put in a simple two-tone cosine into this nonlinear system as V in, and we'll see what we get for V out. And if you actually go through here and do the math, you can see that when we cube this third term, it causes what we're particularly interested in. The squaring of the two-tone term actually provides this term here in these cosine squared terms. If we use our trigonometric identity, a cosine squared of x gives us 1/2 plus 1/2 cosine 2x. Right? And if we have cosine A, cosine B, we get 1/2 cosine A minus B plus 1/2 cosine A plus B. We get the sum and difference of the arguments of the cosine. And so what happens here is we actually get terms generated at the second harmonics of omega 1 and omega 2 as well as DC. This term actually gives us omega 1 minus omega 2 and then also omega 1 plus omega 2. But what comes really interesting as far as, so this is actually going to generate some things that are down near DC and also at the second harmonics, which aren't close to our main band, so we can easily get rid of them if the system is frequency selective enough. But this other term here, this third order term, actually multiplies the squared results against another iteration of these linear results. And so we get these two terms here. Now we have the cosine squared and the cosine. What this actually does is it gives us terms at 2 omega 2 minus omega 1 and 2 omega 1 minus omega 2. Which, if you think about it, these frequencies are going to be right next to the original tone frequencies of omega 1 and omega 2. So if I run omega 1 and omega 2 through this third order nonlinear system, then I have terms that come out just above and just below the tone, the two initial tones, separated at the same frequencies that the initial tones are separated by. Now this is problematic because we're right near our transmission band, so it's very hard to make our amplifier frequency selective enough to be able to get rid of these. And there are results in nonlinearity. So the more nonlinear we get, it turns out as we increase the input power of our initial tones by 1 dB, we will get a 3 dB increase of these adjacent tones. The third order nonlinearity causes a 3 dB increase of the adjacent tones for every. So as we go further and further into compression, what's interesting is we get more and more adjacent channel power. And this could be the band where the neighboring communication system is trying to operate and we just destroyed its constellation as we showed in the first slide. So this gives us a correlation of the fact that if we can maximize linearity, if we can improve linearity, we can get rid of these third order tones. However, we've learned already that linearity and efficiency are a tension, right? So to maximize the linearity, we have to decrease the efficiency. And we really don't like to do that. But there are some, so basically now if you think about, let's say, any signal, maybe you have a bandpass signal. If you have a bandpass, for example, a chirp would be a bandpass signal, or a CDMA signal would be a bandpass signal. If you have all these tones present at the same time, you can think of if you're a rectangle function signal, you can think of it as a bunch of tones, and all of them are going to do what's called intermodulate, which is what we describe as those two tones that I told you producing as an additional two tones. That's called intermodulation, or third order intermodulation. That's often what it's called in the industry. So when we talk about third order intermodulation, that's what we're talking about. So if we have third order intermodulation of a rectangle function, you can think of that rectangle as a bunch of little tones, and all of them are intermodulating with each other. So they're going to produce two additional functions that spread the same width as the initial tone and go all the way out to approximately the same additional width as the initial rectangle on each side. Now we also get in-band distortion, which is another issue, right? If we were trying to communicate, that could distort our communication system. But for a radar, as long as we know what waveform we transmit, we can process it correctly when we get it back. But the spectral spreading caused by the out-of-band part of distortion tends to be of high interest to us. So how do we get rid of these side lobes? And this comes back to your comment earlier, but filtering can be difficult because microstrip cavity filters over a kilowatt can be hard to obtain. And it can also be very expensive. Now, so what we have focused our efforts on in this work is linearizing the power amplifier. How do we make the power amplifier linear enough to meet the spectral requirements?
Not only that, you need a filter to slow down projection. Linearity, phase linearity.
That's also a possibility which we haven't even investigated, some of the filtering distortions of phase, absolutely. So we want to linearize enough to keep our products below the spectral mask, but we want to try and be as efficient as possible. And this is the plot that I showed you earlier, just reiterating that when the gain starts to decrease, the efficiency is maximized. So what I want to do is discuss, I'm going to take you into the power amplifier world just to give you a little on my background. I'm a microwave guy. I grew up in the microwave world. I did my PhD in microwave transistor modeling. Went to Baylor University, talked to Larry. He got me involved in radar. So I had to learn radar, but microwaves is my home. But as we've discovered, applying microwave technology to radar can be a useful thing. So these are some terms that are thrown around in the microwave community all the time that a lot of radar engineers may not be familiar with. So I'm going to go through and carefully define them so that we understand them before we start throwing them around. These are ways to measure efficiency. So I'm going to talk about ways to measure efficiency in linearity. The drain efficiency is commonly used. That looks at the RF output power of an amplifier divided by the DC power put in. I don't particularly like to use that one because it doesn't consider the input power at all. So it has nothing to do with the actual power gained by the amplifier, it just looks at the output power. I like this one the best, and this is the one that I'm going to use. It's the power added efficiency. It's often called PAE. And it looks at the output power in RF minus the input power in RF divided by the DC input power. The reason I like this is in the numerator we have the additional power that is thrown into output power of the amplifier, and we divide it by the DC power, which is our source of power, to create that additional power. Right? We have the Pn as a baseline, that's in the numerator. We've got to get some additional power to make the output power greater than the input power. Where does that power come from? It comes from the DC power. So we have a numerator, which is the additional power we gain, over the denominator, which is the additional power we put in. We multiply that by 100%, we get the PAE. We want it to be as high as possible. We could look at this overall efficiency, which is another metric that shows up in the literature, but we won't consider that in our work. We'll be looking at this one today. This gives you a few common metrics. There's also several metrics for linearity. The one that you'll see us use a lot today is the adjacent channel power ratio, which is the one shown on the top. That's the ratio of the power in a specified band outside the signal to the power in the band. So let's just, and this can be defined however you want to define it. So basically you would set this up on a spectrum analyzer. You could actually set channel boundaries. If you use spectrum analyzers, you can set channel boundary for your main channel, your adjacent channels, and then your alternate adjacent channels. And where you set these limits, it will actually add all the power inside those limits, and it can create ratios. So the ratio, the adjacent channel power ratio, just looks at if I'm operating in this channel, and this is my neighboring band, maybe this is a wireless Wi-Fi system, and I want to understand how much interference, I can label the band as this, and take the power in that band, and take the ratio into the power that I'm transmitting in my regular band. And I'm going to try to minimize the adjacent channel power ratio, which is minimizing the power sent to my adjacent channel. It's that simple. Other things that can be used, which I'm not using in this work, but are very legitimate, is error vector magnitude. Now this actually looks at the distortion of the communications waveform and how far it's off in terms of its magnitude and phase. And this would be good to look at a message, but we're not really looking at this byproduct. We're interested in spectral spreading for this particular study. Carrier intermodulation ratio, this could also be used, but this has to be measured using a two-tone intermodulation test, whereas this is looking at a broadband signal, which many of our radar signals tend to be broadband. We've used Chirp waveforms and CDMA waveforms in most of our work, which are broadband signals, so the ACPR is useful. The C to I and ACPR measure essentially the same property, the same nonlinearity property. And then we have noise power ratio, which is another method of in-band distortion. I want to talk about amplifier classes. This goes back to your electronics course in the university, and when I teach RF and microwave circuits, I talk about these. But this you can actually, by where you bias your amplifier, affect heavily its linearity and efficiency. And you can think about this as the following. It was explained to me as a student that the IV curves, the limits of the IV curves, serve as a playing field for the device operation. So we would place the device at a bias point, which is its center of operations. So for a Class A amplifier, I'd label this A, that would be its bias point, or its operating quiescent point. And as we put in an input voltage, a gate voltage to a FET, for example, a field effect transistor, we would change the curve that we're operating on, and we will also change the drain voltage and drain current, ID and VDS, based on a load line. Remember the concept of a load line being 1 over the load impedance. Now if that impedance is resistive, it will be a simple line. And the optimum load line for output power, let's just say we want to maximize our output power, what we would do is we would take our load resistance and make it so that we could maximize the distance we can run without hitting the boundary. It'd be like going corner to corner on a football field or a soccer field, right? You go from one corner to the other. That's the longest distance you can run without hitting a sideline or a boundary. And so we can actually do that here. We can since the slope is 1 over RL, the load resistance, we can choose RL such that we hit the corners. If this maximum is given by the maximum current the device can put out, and this is given by the knee voltage of the IV curves, this limit is given by breakdown voltage, and this limit is given by the zero current. So we can choose our load line. If we add capacitance and inductance, we create a hysteresis in the load line, to where the load line becomes an oval instead of a straight line. I believe if you have an inductor, you go around this way. If you have a capacitor, you go around the opposite way. So you can think about this as a load line. Now, Class A has great linearity. It's a very linear operating point. Why is that? Because we can run equally long in both directions without hitting a boundary. So when I input my voltage, I'm going to get a current that has the same running in both directions. It will have a full wave. It will have a full conduction angle. And it will not get clipped in any way until you make the signal large enough that it's hitting the boundaries on both ends. Now what we can do if we want to increase the efficiency is we can, so the maximum drain efficiency we can get, I'm using drain efficiency here because that's how it's classically presented in textbooks, is 50%. If we want to increase the efficiency, we can actually pull the bias point down to where we're operating right at the threshold of the gate voltage. Now I can run one direction without hitting a boundary, but when I come back here, I'm only going to have a half of a cycle of current, because my second half of the cycle is going to hit the zero current limit. So I'm going to have a clipped waveform. Now what does that mean? Harmonics, right? If I have a clipped waveform, I've got all kinds of harmonics in my signal. That's nonlinearity, right, when I'm generating harmonics. What if I have a third order nonlinearity as a result of this? Spectral spreading, right? So you see the tension here. I can actually make it more efficient. I can go below threshold, which means that I've got work to do before I can even peak above threshold and have just a little small peak of my RF signal, right? And I could still put in a large amount of power so that I peak up to the maximum there. But if I do that, I'm going to hurt my efficiency or linearity even more. So you can think as I go down from class A to class B and then further on down to class C, I'm reducing my linearity and improving my efficiency. A lot of people have used this class A-B point as a compromise between linearity and efficiency. And then there's additional higher order modes of class E and F, which I'm not going to get into, but they're very cleverly designed switching modes where you can even improve the efficiency further. But the point I'm making with this is a lot of people have juggled this, and the bias point is very heavily, the linearity and efficiency are both heavily dependent on the bias point of the amplifier design. Now I want to move on and now talk about more advanced topologies. And I want to note that this discussion is based, I had to learn about this to be able to present it. So I did some work and I went through an excellent series of articles, and also an article in the IEEE Transactions on Microwave Theory Techniques, a four-part series by Rob and his co-authors in High Frequency Electronics magazine. So I wanted to cite this. I've cited this here in these pages, and you can go look at that. I suggest you do that. It's an excellent article in a series of articles. Okay. Pre-distortion is one way to improve linearity. This is a linearity improvement technique. And the idea of pre-distortion is very simple. If you have a nonlinear power amplifier with an output versus input power characteristic, and if my slides vary slightly from what's shown, please forgive me for that. There were things I needed to add and some research improvements that we wanted to insert in updates to what we have. So most of these slides probably follow what you got in your notes. There may be some slight differences between them. Pre-distortion looks at the, so if I have a nonlinear amplifier here and I have output versus input power here, and you can see it's compressed, right? As I increase my input power, I stop getting an equal increase of output power. That causes nonlinearity. But what I can do is I can put an inversely shaped pre-distortion filter in front of this, where it has an inverse output versus input power characteristic. So when I multiply these two together, I'm going to get a straight line. Now, you can probably easily identify what the problem with this is.
How good are you able to do that in practice? I mean, in terms of actually getting this reversed to mine?
It can do, you can use a lookup table. It's pretty accurate. So some people have done very good work with the pre-distorters. One thing you have to be careful about is losing efficiency with the pre-distorter, but you are doing this on the input, so you're not looking at the output power wave of the pre-distorter, so it does help. And this is actually a commonly used linearity enhancement approach, and usually when you see pre-distortion, it's used with one of the efficiency enhancement approaches, such as envelope tracking as well.
Are you referring to the use of the arbitrary waveform?
You could, yeah, absolutely. You could pre-distort the input waveform based on what you know you're going to get out. That's usually what's done here. Although I haven't done personally any work in this type of pre-distortion, that's from what I understand, that's how it's done. You pre-distort the input waveform to adjust for the linearities of the nonlinear system so that you get the waveform out that you want. It's effectively doing this. It's looking at the nonlinear characteristic and compensating for it. So Rob states that 10 dB improvement can be given by 10 dB improvement in the adjacent channel power ratio can be accomplished by pre-distortion. That's significant. Later you're showing those masks that were 40 dB down. You can get 10 dB from doing this method. You can even adjust for memory effects if you want. Now, digital pre-distortion allows continual updating for even changes in the device, which is great. But it requires a significant amount of memory, so your computing requirements can be fairly hefty with this. But it's worth it if you can get good feed forward is a linearity enhancement technique. It's actually a clever little technique. If you think about it in terms of the two tones, you can put your two tones in here. It causes distortion, so the other two tones come out. But you take a little bit off from a divider of those two tones. You run them through a phase shifter to compensate for the phase change of the amplifier. You get your two tones here. you take the main signal off with its additional 2 tones and you subtract the initial signal. The copy of the initial signal. So what you get out of that is just the 2 distortion tones. You run that through a phase shifter and linearly amplify it, and then you subtract it from the main signal. So you're actually, if you can get all these phase shifters and amplification factors correctly, you can actually subtract the distortion tones out after the nonlinear amplification is done, and you end up with your initial 2 tones back. Now there is a cost to be paid. This linear error amplifier requires bias, which means that we're taking a hit in efficiency, right? The other thing is, these couplers cannot operate efficiently very well either. In fact, as I'll show later, 3-port network can't be lossless, matched, and reciprocal at the same time. So anytime you see someone draw a summation tool or a summer, be very, very skeptical of that. It is impossible to implement a perfect summer at microwave frequencies that is lossless, matched, and reciprocal. It's not even a microwave property, it's actually a property of general circuit theory that a system can't be lossless, matched. A 3-port network can't be lossless, matched, and reciprocal. If you add a 4th port, you're obviously losing power to that port. Feed forward can reduce distortion really well, 30 to 40 dB, but as I mentioned, we can lose efficiency. Also, the system components have to have good bandwidth, and we need good amplitude and phase matching, and we don't want drift in our system. If temperature causes drift in our systems, we require on some very precise amplification in these other legs of the system here to be able to make sure we get this distortion canceled. And you might need a control system to maintain accurate correction. What's so bad about that? Well, more power, more memory, more size. Envelope tracking. This is a common technique. I really encourage you to go look at some of the work of Professor Zoya Popovich at Colorado. She's done some excellent work implementing envelope tracking for the power amplifier. This is actually an efficiency enhancement technique. In this article by Penny actually shows it very well. If you think about this blue signal here as a signal that you have, that you're amplifying, and you think about your supply voltage as being fixed and higher than the signal, you can see the power you're using is the difference between your supply voltage and the actual envelope of your RF waveform that you're transmitting. Now, this is, and I taught this to my communications class last week, it's very, very interesting. If you look at 16 QAM and you look at 16 QPSK, 16 QAM has a wonderful constellation as far as being able to detect it, right? It has 4 points in each area. Now the problem with it though is all those points have different amplitudes. 16 QPSK has 16 points around a unit circle in the IQ plane. So they're equal amplitudes. Now how does that matter? Well, that affects the front end because in 16 QPSK where they're equal amplitudes, our signal would be equal amplitude and we would put our bias just above the maximum of that signal, so we'd be very power efficient. We wouldn't lose a lot of power. But if we have something where we have a high, what's called peak to average power ratio, where the difference between our peak RF power and where we spend most of our time operating is significant, and we've got a lot of these red areas in our picture where we're losing power. And so what envelope tracking does is it actually changes the supply voltage based on the changing envelope of our waveform. So as we change our waveform, we have an envelope detector that actually, I'm sorry this is so fuzzy you can't see it, but here comes the envelope. We will actually have an envelope detector that detects the envelope of the signal and feeds this into a power modulator. And it changes the DC supply sent to our power amplifier. So what we're actually doing is we're sending in a lower supply voltage at the moments that our signal has a lower amplitude. We're sending in a higher supply voltage at the moments our signal has a higher amplitude. This is a very efficient way to do things. I mean, there's some buck boost converters that require power, and but it's actually used quite a bit these days. This is a very popular technique for efficiency enhancement. In fact, you see the pre-distortion envelope tracking combination a lot these days. The pre-distortion for dealing with the linearity, the envelope tracking for dealing with efficiency. Yeah, there.
I think Samsung is the last larger, and that's what I look at the later switch is using that in power amplifiers in the latest phones.
Really? Okay. Are they using pre-distortion as well?
Envelope tracking.
Okay. I know it's very commonly used technique.
But how does this envelope tracking perform in terms of the support of power and distortion?
Oh, the envelope tracking actually enhances the efficiency. And what's interesting is if you look at most of these techniques, they deal with one problem or the other. Like, for example, pre-distortion doesn't deal with efficiency, it just deals with linearity. So you may lose efficiency by using pre-distortion, and then you may have to adjust. But the good news is you can use some of these techniques in conjunction with others. And that's pre-distortion and envelope tracking are commonly used together. So what you can do is you could pre-distort the waveform to help the linearity, and you can use the envelope tracking to help the efficiency. So the other thing is the envelope tracking also is reasonably good at keeping things linear because it does make sure there's a slight barrier between your supply voltage and your signal waveform. So in essence, you are holding the supply higher than the signal, which by definition should mean you're not clipping the signal and you're maintaining linearity, unless of course you're using class B or something. So that's a good question. So in the con technique, envelope elimination and restoration, you can actually take the envelope, the amplitude modulation off, run it through a high efficiency power amplifier by saturating that power amplifier and then put it on at the end. Put it back on at the end. That's another way to improve efficiency. Then we mentioned Doherty. Here's Doherty. This is the Doherty configuration. You actually have two amplifiers in this configuration. You have a main carrier amplifier and a peaking amplifier. And the carrier amplifier is used all the time. But what you do is you have a lower power supply on this one. So that for a lot of the lower signals, you don't even use the peaking amplifier. You just use the carrier amplifier. Now the peaking amplifier, you can make this a deep class C operation, which means well below threshold. And so your bias doesn't allow any current to be conducted during its DC bias. And what happens is only if the signal is very, very large will this peak above the threshold. So when you have a very, very large signal, you're going to be saturating the carrier amplifier, and then the peaking amplifier will just kick on enough to bring the signal above threshold. So what happens is as you add these two signals together, you'll get the brunt of the signal here, you'll get the upswings here, and you'll get the peak coming out of the peaking amplifier. And then when the signal goes back to lower power levels, the peaking amplifier will turn off again because it's biased below threshold. So that's how the Doherty works. And the idea of this is you can use less power to bias the carrier amplifier because you don't need to worry about its linearity. When you get those high peaks, the peaking amplifier will take care of it. You'll only be spending bias on the peaking amplifier when it's needed to accommodate large signals. This is really commonly used too. If you go to the microwave conferences, you'll hear entire sessions where they pretty much talk about Doherty amplifiers. This is a common technique. Link. Link is a technique which Larry introduced us to and wanted us to take a look at, and so we did. This was the work of a lot of work with my former graduate student Laura Wong, who's now at the Air Force Research Lab in Dayton. And she did a lot of work on this, and it's linear amplification with nonlinear components. It's a clever technique. Unfortunately, it's a representation of the fact that you can't have your cake and eat it too, which is a common American phrase, and this is a good technical representation of that. So we have two amplifiers in the link, linear amplification of nonlinear components. And what we do is if MFT is the amplitude modulation, we actually hide the amplitude modulation inside the phase. So we put this omega of t as the frequency modulation plus the carrier term. We have another term inside the phase, which is the inverse cosine of the amplitude modulation. Now the reason, and then here we add it, here we subtract it. This is, and what comes out is actually based on trig identities. So if you have two cosines and you add them together, using the summation tool, you actually have cosine A, cosine B is equal to cosine A plus B plus cosine A minus B. So this is A, and omega t and B would be the inverse cosine here. And so by virtue of this trig identity, you end up taking 2 times G times the cosine of the first term, omega t, times the cosine of the second term. So you end up with the cosine of cosine inverse of M of t, which gives you M of t, the amplitude modulation, out in front on the amplitude, right where we want it. So this looks beautiful, doesn't it? Why does it look good? Because these have constant amplitude. So constant amplitude signals are good for high efficiency because we can set the bias for both of these amplifiers right at the point where this will drive it into high efficiency, and we don't care about amplitude distortion at all. And then we recover our amplitude on here. It looks beautiful. There appears to be no hitches except for a little hint I gave you earlier. Remember I told you always suspect when you see this in a block diagram. Right? because it can't be lossless, matched, and reciprocal. We have to figure out a way to implement this. So we actually tried, there's several different ways to do this in the literature. One is the 180-degree coupler, which is a 4-port network. Now, a 4-port network has a 4th terminating port with a resistance on it. So by nature, you can think about that as the possibility of loss, right? If you have a termination resistance and you dump power into that port, it's often called the dump port. If you send power to the dump port, you're losing it. So that creates loss, but it will be matched and reciprocal. The Charest outphasing combiner is lossless, but it causes, it's not going to be matched at all the ports, and we'll see that in the issue. So we did it quickly. Look at this. I'm going to breeze through some of these. You can look on them at their own. But for sake, I want to go to some of the more innovations that we're working with. You can see here we tried the 180-degree coupler. It's matched and reciprocal, but here's the 4th port. You can see this delta port here. The dump port is connected to a 50-ohm resistor usually. We have to dissipate power. Here's the Charest. The Charest is an interesting technique because it actually does this only with transmission lines that are lossless. The problem with Charest is, as the amplitude changes to one of the amplifiers, or the idea is these signals phase, right? Their phases are going to outphase. That's basically what happens is the phases of these will change based on the amplitude modulation. We'll add a different way to create the output. As the phases change, it turns out we'll actually be showing a different impedance to each amplifier. Each amplifier starts loading the other one. And that causes issues with amplifier linearity performance. And it also causes efficiency issues because the load impedance seen by each amplifier changes, and we actually get power reflected back into the amplifiers. So we did a design, and we did a load pole and a source pole, which means we tried to find the load and source impedances to give us the best efficiency. And we did that here using a model with its model. And we go through some of these results. When we were done, just to test our work, we designed a Charest and we designed a 180-degree coupler. Both showed their optimum efficiency impedance near 50 ohms, which is what we wanted. And then we took this curve, which is kind of the money curve, so to speak. This is the one that tells you about the performance. If you look at the transducer power gain versus the input voltage, we would expect that if we were a linear system, we would expect a perfect parabola because we're looking at power gain versus voltage, and we know power is proportional to voltage squared, right? So we would expect a perfect parabola, and we got a perfect parabola for a 180-degree coupler. We didn't get such a perfect parabola for the Charest. You see a slight offset, and this is a linearity issue. We presented this paper at the 2010 WAMICon, Wireless and Microwave Technology Conference. We actually did a paper on this. We showed this study. So they have similar efficiency. Now, why do they have similar efficiency? For the Charest, the power ends up being reflected back to the device because each amplifier loads the other one differently as the amplitude's increased. Now that's actually bad because we can't do anything with that. It's going to be reflected back to the device, it's going to be dissipated as heat. Gone. If we use the 180-degree coupler, the extra power actually gets delivered to the 50-ohm dump port here, shown as the delta. You see the delta in the sun is going to go out our antenna. So as our amplitudes change, we'll have a different amount go to the summation port, which sums the two signals. As our relative amplitudes change, the relative phases of these two change, right? As the amplitude modulation changes. So we could actually change addition to subtraction if we were 180 degrees out of phase based on a message of 0, and all our power would be going to the dump port. And that's what happens. And so we end up costing ourselves efficiency there. The good news is that since the power is not reflected back into the amplifiers, it is delivered to a load, we can try and make this load a power rectification network that could then be delivered back to serve as bias power for the devices, and some people have done work on this. So linearity and efficiency. Just to wrap up what we've talked about, and feel free to ask questions at any time. Power amplifier nonlinearities are responsible for both spectral spreading and distortion. We've shown some techniques about linearity and efficiency. And many techniques are very limited because a 3-port network can't be all 3 reciprocal matched and lossless, as shown by this Link and Charest study. And the Link study shows that outphasing has some flaws, but I'd rather use a 180-degree coupler than the Charest network because the 180-degree coupler, at least we can do something with the port power and it demonstrates good linearity, whereas Charest is doubtful in both. So anytime I see an outphasing paper presented at a conference, I'm very skeptical of its success. So if you're presenting an outphasing paper, make sure I'm not in your session because I'll probably ask hard questions since this study. Okay, so that's kind of a good stopping place. If anybody's got questions to ask before I jump into this next concept. Do the idea of basic linearity and efficiency enhancement make sense? All right, so this does kind of turn a corner here. And then most of the stuff I've talked about is stuff that has been out there for a while. This kind of brings us up to some power amplifier terminologies and ideas that we can use. But now I'd like to talk about where does the future lie for radar and how does that affect us as transmitter designers if we're working on the transmitter amplifier. Cognitive radar has been an area of interest, and Sebji has been talking about that. Simon Haken and Joe Gersey were heavily involved in the proposition of this. And a cognitive radar senses and adapts to its environment. An adaptive radar is capable of adaptation. A cognitive radar basically can somehow sense the area around it and change to match it. So I think of cognitive and adaptive radar together. And actually, if you think about it, Bob and I have been talking, and Larry and I have been talking about this, and if you think about the future environment of radar and communication sharing, at some point there's going to be this, everything's going to be adaptive. The frequencies that they transmit at are going to be adaptive. If you've heard of the term dynamic spectrum access, that's the idea of very little of the allocated spectrum is being used at any given one point in time. I heard anywhere between 20 and 80% of the spectrum, depending on the environment. So even the densest environment still may have 20% of their spectrum available. Dynamic spectrum access says if someone's not using their spectrum, you can use it until they're ready to use it again. And this could actually allow us to more usefully use the spectrum. However, there are very significant hardware limitations for this, because a power amplifier is, you know, if you've designed ICs or amplifiers or anything of that nature, it's tuned to operate at a certain frequency or a small frequency band. And what happens if it has to jump to a different frequency band? If the system says move, your microwave hardware has to be able to make that reconfiguration. This is where a lot of signal processing folks don't understand. The transmitter design must also be reconfigurable and adaptive if your system is going to be reconfigurable and adaptive. So if we're designing reconfigurable and adaptive radar communication environments, then we have to have an adaptive radar, which means we have to have an adaptive and reconfigurable power amplifier. So that's what I'm talking about now, is I'm going to talk about ways to reconfigure your power amplifier and algorithms that we've designed to do this for future technologies that will be put in future radars. Now how this is implemented, we haven't gotten that far yet. Right now we're actually using a laboratory measurement system, which I think there's a picture in a few slides here that shows that measurement system to illustrate the future system. And here's the picture of our future radar transmitter that we believe is going to happen. It'll be controlled by a brain. It may not be an FPGA, it may be something else, but there will be a brain that controls it. And it will influence the signal generator, which all this will be on the chip and under the FPGA's control. So it'll influence the signal generator. That means it can tune the waveform. And it will influence the tunable load network, so we can change the load impedance or load reflection coefficient shown to the device. And it will also contain measurement capabilities to measure the spectrum to see if it's spreading into the adjacent channels, and measure the power so we can see what the efficiency and output power levels are. Now right now all this is in the laboratory. We have a load pole tuner that we're using for the tunable load network. So we have a Mori microwave load pole set up where this mechanical tuner has a couple slugs that move up and down. It's a fairly bulky piece of equipment. We have a big key-site spectrum analyzer, a key-site signal generator, and a key-site power sensor sitting on a lab bench right now. But we're designing algorithms to where this can all be put on the chip eventually and done in real time. So I want to show you a series of algorithms and approaches that we've used. Now where we're starting is we're looking at simple algorithms to optimize the circuit. Where we're going is a joint circuit and waveform adaptation method. I'm going to start from the circuit end. Bob's going to start from the waveform end and describe some of the waveform approaches that we've been doing. And we're going to meet and we're going to show you where it's going to put them together. Does that kind of make sense, the framework we're going at here? So I want to start talking about one of our first impedance searches. Actually, this isn't the first. The first one I did an output power optimization search during my PhD work, actually. And that was published in a journal. But this one is more appropriate for the type of radar thing. Larry mentioned this in his part of the discussion, that we need to be able to try to optimize the efficiency of a radar while meeting adjacent channel power constraints that would be dictated by a spectral mask. So that's what this does, and you can see the publication information there if you'd like to go look at it. It recently came out in the journal. Now, so we're really thinking about this as a Pareto optimization. A Pareto optimization is simply an optimization in which a trade-off is involved. And we know that to be true of linearity and efficiency. And actually, has everybody seen a Smith chart before? I'll be glad to explain a little. And you know the Smith chart? The Smith chart. Okay, so the Smith chart is a collection of all load impedances. Basically, that's what it is. In fact, it is the complex reflection coefficient plane, right? Where the vertical axis of that plane is the real part of the reflection, or the imaginary part of the reflection coefficient. The horizontal axis is the real part. And so we can optimize the reflection. It turns out as we change the reflection coefficient, which is identical to a load impedance. So we change the load impedance, we change the output PAE performance as well as the adjacent channel power ratio. And we can actually, one way to do this is what's called a load pull measurement. A load pull measurement actually changes it pulls the load. It changes the load impedance and it measures the efficiency or adjacent channel power ratio or whatever we want to measure and then fits contours to it. So the curves here are actually load pull results for power added efficiency, PAE. So the optimum power added efficiency impedance is here, reflection coefficient is here, and you can see the contours showing that you descend as you go out towards the edges. It also shows that the adjacent channel power ratio is a significant function of the load impedance. We can also load pull for ACPR, and those are the blue curves, and there's the optimum there. It's a different place in the curves once again go out. And now if we're interested in great ACPR and we don't care about the power added efficiency, we're gonna put it right here, right? That's the ACPR optimum. But if we care more about efficiency, we're gonna optimize here. If we care about some combination of the two, we're going to move along this trade-off line here, right? We're going to go, as we start caring less about ACPR and more about PAE, we move from the one optimum to the other. There's actually a Pareto optimum locus that goes between these 2 points. And so what's going to happen is usually in a Pareto trade-off, you're going to set okay, I must have better than this in one case, and then you're going to try to optimize the other case while meeting your constraint. You'll constrain one of the objectives and try to maximize the other. So for our case, usually we're not really excited about getting great ACPR. We're only doing it because the regulators are making us, right? We have to keep our adjacent channel power lower because the regulators tell us we have to. We can't interfere with the system in the next band. So what we are doing in most of our tests is we constrain the ACPR. We say that the adjacent channel power must be below some level, and then we try to get the best efficiency we can, the best PAE we can while meeting that constraint. And this is very applicable to a real-time reconfigurable radar application. So what we did was we said this takes too long to do a full load pull, right? If you're trying to reconfigure your radar in real time, you don't have time to measure all of the impedance states on a Smith chart and then figure out where the maximum is. So we want to get there as quickly as possible. So what we did was we devised an intelligent search. And what we do is we start at some given candidate, arbitrary candidate in the Smith chart, and we measure the change in ACPR and PAE as we go just to the right and just above. And we can estimate the gradients from these points over the two-dimensional Smith chart for ACPR and PAE. And these give us unit vectors that are in the directions of steepest ascent of the PAE and also the angle bisector. So here are some pictures of how we go forward with our search. So if we can estimate the gradients based on those previous tests, we start at candidate 1. We would take 2 surrounding points, we'd estimate the gradients. Let's say those gradients are PAE represented by a P hat and ACPR represented by A hat. What we do then is we take a jump in the direction, and I'll explain why we choose this. We actually superimpose combinations of this ACPR gradient and the bisector between PAE and ACPR. Now let me talk about this bisector for a second. The reason the bisector between PAE and ACPR is so important is if a point is on that Pareto optimum locus, remember the Pareto optimum locus I showed you? That means it's the set of solutions where we have the best trade-off for some constraint between the two. If it's on that locus, the PAE and ACPR gradients will be collinear and oppositely directed. will be like this. Right? If you think about it in terms of the contours will be collinear as well. If we have an ACPR contour and the PAE contour, it turns out that the Pareto optimum locus goes through the points where the two contours are collinear. And if the contours are collinear, we know those are the level curves in optimization terminology. The gradients are always perpendicular to the level curves, so the gradients will also be collinear to each other. So we use the ACPR and PAE vectors. The angle between them is actually a measure of how close we are to the Pareto optimum locus. How close we are to the trade-off locus of the solutions. So if these are closer to, if they're 180 degrees apart, we're right on the Pareto optimum locus. If they're not, we're away from it. If they're like this, we're a long way away from it. So we actually use that as a measure here. You see this theta here? The theta is going to be the angle between B and A. So when theta is 90 degrees, which then we actually define theta target as 90 degrees, we assume we're on the Pareto optimum locus. So we will introduce a component into our search vector on the bisector angle to try to get us towards the Pareto optimum locus. And the magnitude of that will be dependent on how far away we think we are. How different is our angle from 90 degrees? If we're on the Pareto optimum locus when the angle between B and A is 90 degrees. So that's what this dB is. That's how much we weight this vector in the summation. Then we also are trying to get to the ACPR optimum. We go towards the ACPR optimum, but we want to get to ACPR target. ACPR target is the limit of ACPR. So if we say we need ACPR to be lower than minus 27.5 dB, that's my regular voice, right? If we need ACPR to be lower than minus 27.5, then ACPR target becomes minus 27.5 dBc. And we look at how close we are to that, and based on if we're farther away from that, we make our ACPR component greater. If we think we're closer, we make it smaller. We superimpose these. And so our search vector allows us to walk in a combination of towards the ACPR limitation point and the Pareto optimum locus. If we get to the ACPR limitation point and we're on the Pareto optimum locus, that's going to be our desired solution. Right? Because the Pareto optimum locus, remember, is the point, it's the compromise of best trade-offs. And when we're on the ACPR limit, we've got the best PAE to stay within that ACPR limit. Okay? So inside the acceptable region, that means if we have acceptable ACPR, we actually flip this. We start going back towards PAE optimal. If we already have better than ACPR than E, then we put this DA with the PAE vector. So we go backwards. We can actually decrease our ACPR and improve our PAE behavior. Okay? And we have some, at the end of the search, if the next candidate is outside the acceptable region, or it has a lower PAE than the previous candidate, we divide the search distance by 3 and repeat. So as the search distance parameter gets smaller, we keep going. And we end the search when the search vector magnitude that's proposed for the next step is below a resolution neighborhood point distance. It's less than the steps to the gradients. So anyway, I want to show you the results. This is a traditional load pool. We found the Pareto optimum for a given ACPR limitation that we chose to be this point. And here's the PAE optimum. Here's the ACPR. We did these simulations with monolithic models. And I want to compare the results of a traditional load pool to our algorithm, which started at a reflection coefficient of 0.9 at 180 degrees. So here's the traditional results. It shows that the point is right here. Here's our intelligent algorithm. It's very close to that point. The limitation here was being less than minus 45. We got to minus 46.25 in this case. And we got a very good PAE. And here's our results for multiple starting points. This shows another one of those starting points. You can see we, at this time, decided to start at the bottom of the Smith chart. We got to almost the same point in 11 measurements. So rather than having to load pull the whole chart, which would take tons of points to have great resolutions, now we can go from a point quite far away in the chart to the best point. Look at this measurement spread. This is great. It's between about 10 and 30 measurements, depending on where we start and what the settings are. If we knew something about what we were doing, we could probably decrease this even more. We're doing this totally blind, assuming we know nothing about the search, what I would call a dumb search. We tried this on the measurement bench with our Morty Micro ATS load pool setup, and here are the measurement results for a traditional load pool. You see these green crosses here? Those are all measured states. So that's a lot of measured states. I haven't counted them right now, but it's probably 60 or so, at least. And you can see there's our optimum. And you can see our contours have a lot of jitter in them, partly because we don't have a real fine grid, and partly because there's some measurement noise with lower ACPR values. And that's where our rough estimate is. And you can see our resolution isn't all that hot here. It does interpolate between points, but we don't have a lot of points measured near the optimum. Then you come over here to our algorithm. You can see we got to almost the same point, 22 measurements traveling across the entire Smith chart using this gradient-based algorithm. And our limit was minus 28.2. We're very, very close to that limit, but we are below it. So we are in compliance. And our PAE is maximized. Now this doesn't have that great of a PAE, it's only 6%, but we were actually doing these experiments on a low noise amplifier, which goes to show it's the technology of the algorithm we're testing, not the actual technology of the device. We could do this better for a power amplifier or some type that was designed for high efficiency. But we're just throwing a packaged amp that we had in our lab out of the bench and load pulling it. So here is the measurement from multiple starting points. You can see once again in the measurement we had a low number of points. Notice that our ACPRs are all just below minus 28.2, which was the limit. And our PAE numbers all correspond very well to power and efficiency. And our end reflection coefficient results are all in the neighborhood of each other. There is some variation, but that's based on the fact that we expect that. It's the contours here, as you can see. You can think about the PAE as a hill. And as we get near the maximum, the hill flattens. So we have very similar PAE at a fairly wide distribution of points. So the PAE values are what's really important to look at here. Do our final PAE values correspond well to each other when they do? And we're in the relatively same neighborhood. A lot of people ask us about local minima of these searches, or local optimum. Is it possible we could converge to a local optimum? Certainly it's possible, but we see that this thing actually overcomes noise and measurements in local optima very well. This technique seems to be fairly not as robust as we believe it could be to those types of issues. The other thing is because we're constraining ACPR, usually we force ourselves toward the global optimum because we have to have a certain amount of ACPR for it to even be playing as our optimum. We did a previous algorithm where we actually, and this was the work of my previous student, Josh Martin, we actually did a two-step search algorithm where we went for the optimum of PAE first and then tried to walk down that Pareto optimum locus slowly. And we've been able to decrease our number of measurements by about 40 to 50% from all these starting points. So this was a good find for us. So any questions on that before I jump to the next innovation? Okay, this is very similar, so this will kind of drill in the same idea, but we started looking at the question of, well, ACPR is great, communications people use it a lot, but in reality, as Larry and I have talked about, it's the spectral mask that we're limited by. It's actually a spectral mask. So we asked the question, could we replace the ACPR criterion in our search with compliance with a spectral mask? And it turns out we can. We created a spectral mask compliance metric that did this, and we've published this. It appeared just recently in January of this year in the Transactions on Aerospace and Electronics System. You'll notice we're publishing our work in the radar journals, and we feel that's where it belongs. We really want to make these, our goal is to make these available to radar engineers to use in radar systems. So spectral mask-based optimization, this is what I mentioned, is that it's better than ACPR as far as this is where the regulator is going to knock on your door, give Larry a call from the State Department telling that there is spectral violation. So this actually optimizes directly to the end user requirement. And it is a useful measurement of nonlinearity artifacts, but it's usually used to determine spectral compliance. So this may be more useful. So here's the metric that we introduced. This was designed by my PhD student Matthew Fellows, and most of this work was done by him, very ably. But it's the maximum over all frequency measured points that we look at of the spectrum itself in dBm, power value measured by a spectrum analyzer, minus the mask value in dBm. So basically, we take this difference, spectrum minus mask, at all measured points, and we take the maximum value of that, which is arguably either the worst violator or the closest to the line, right? if you have 10 kids and one tends to misbehave more, he would be closest to the line, right? Or maybe your worst violator. It's funny, in our research group meetings, I compare a lot of these techniques to child rearing techniques, and my graduate students think I'm off base, but maybe if this doesn't work out, we may start applying some of our techniques to drawing boundaries for kids and allowing them to optimize their performance without going outside. Anyway, I think that's a joke that we should.
So how many kids do you have then?
0. Yeah, that's exactly right. When you have kids, you realize these techniques aren't applicable because kids are nonlinear systems.
Yeah, I have 3, and I like discipline, but
Okay. I think I'll find some of these techniques applicable then.
We have one.
You have 1?
I have 2.
You have 2? Oh, good. Oh, that's great. Anyway, so let me iterate here what happens. This is the worst perpetrator. Okay, so let's also look at this situation. It's very easy to tell whether our spectrum's in compliance, because S sub m is the maximum difference over all points. So if S sub m is greater than 0, that means we have a point at which the spectrum is higher than the mask, right? So that our difference is positive. If the S sub m is less than 0, then we're completely in compliance. So we can tell directly by this number if we're in or out of compliance. So remember we had the ACPR boundary for our optimizations? What do you think our goal is going to be for spectral mask compliance for this S sub m metric? We want to be as close to the line as possible without violating. Right, which your kids do too, right? They want to be as close to the line as possible without getting punished, right? Where is that going to be? S sub m would have to be 0 because the spectrum minus mask would be equal to 0. So we're going to try to get S sub m as close to 0 as possible, which means we're allowing our device to operate as efficiently as possible without violating the spectral mask criteria. Now, Professor Shannon Watt has done a lot of good work on a spectral mask metric that he has. There's a reason that we don't think it's quite as applicable here, although it's very applicable to the work he's doing. And he actually integrates the difference between, and uses a signal energy type of approach to the difference between the spectrum and the mask. However, in this case, that wouldn't give us a clear answer of whether we're in violation or not, because we could violate in some points and we could have very good compliance in other points that could make the mask or the metric look really good. But we think we need a mask that clearly shows compliance or not for this purpose. So here's a situation, an example of this. Here's a case where S sub m will be greater than 0 dB. This is a fail, right? You see these 2 points where we have spectrum higher than mask. And this is where it's less than 0 dB. You can see all points. And this would be the maximum point here, right, of the spectrum. So this would be the value of S sub m. It's very close to 0, but it does pass. So we did the same thing. We calculated gradients. In this case, we calculated the gradient of S sub m in PAE rather than ACPR in PAE. And we used exactly the same approach. Now you notice instead of an A vector, we have an M vector, which is the spectral mask optimization. And we have a D sub m. In this case, we assume our D sub m target is our S sub m target, which is our spectral mask metric, is 0. So we don't have a minus anything, we know our target is 0. And here's our results for our algorithm from multiple starting points in the Smith chart, all shown on one page. You can see we had 26 measurements coming from the top, we had 11 measurements coming from the right, 22 coming from the left, 10 coming from the middle, and 19 coming from the side. And you can see our optimum here our constrained optimum ended up being in the bottom right of the chart. But still, now we have a spectrum mass metric to measure directly. All 5 cases are under 27 dB, or 27 measurements, sorry. So there's a table that shows the results. You can see our MD are also close, our PAE optimums are close. And look at these NS sub m's. They are very close to 0 dB, right? So we're getting right up next to the regulator's line without going over. That's exactly what we want to do. Now, in a dynamic system, dynamic spectrum access, the regulator may not be a red book like it is now. It's sitting on someone's shelf. It might be a dynamically adjusted spectral mask that the regulator may change in real time. So in that case, what could we do? We could run this optimization again with the new spectral mask and reconfigure the circuit, right? So let's say our ship is out in the middle of the ocean. Now the spectral mask might become less lenient. So we can re-optimize and we can actually improve our PAE and run right up next to that line, right? But then now if we sail to New York Harbor and everybody's using their cell phones, we get a tighter spectral mask, right? So we have to back off away from the line. We get as close to it as possible. We may lose PAE, but we'll still be doing as well as we can while meeting the requirements. Or maybe we're told we've got a jump in frequency and there's only a small band that we can exist between two cell phones, so our mask becomes narrower. Now we really have to reconfigure, we can reconfigure our electronics to do this. So while we might have lookup tables available and that type of thing, the advantage of this algorithm is it can do whatever it's called upon to do, as long as the spectral mask is provided by the real-time optimization network. So this is actually interesting. From our starting point on the left, or on the bottom of the Smith chart, these are our spectra at the start and end points. So this is for this optimization down here. This one here, so there's our start point, there's our end point. In 19 measurements we optimized. Here's our spectrum and spectral mask at the starting point. You can see we were actually out of compliance at the starting point. At the end we were just barely in compliance, which is where we should be, right? Because we're trying to maximize our PAE, which causes us to fail compliance. And we passed the spectral mask. And the next thing that's on our agenda here is the Smith tube for joint circuited waveform optimization. And I showed you the Smith chart, which was invented by Mr. Smith at Bell Laboratories in the early 1900s. This is the Smith tube, and it actually extends the Smith chart in a third dimension. So it's a cylindrical extension of the Smith chart. You can see that our XY plane is still a Smith chart. But now we have a third dimension that we can use for something else, and this allows us to do joint circuited waveform optimization. And this was our first use of the Smith tube, was as a bandwidth Smith tube, where the vertical axis actually represented the bandwidth of a chirp waveform. So this is, remember how I told you we were going to progress from circuit optimization to joint circuited waveform optimization? This is our first iteration at joint circuited waveform optimization. We took a parameter of a typical radar waveform, a chirp. It's a very important parameter as well. Bandwidth it is the main parameter that allows a radar range to be detected. The more bandwidth, the better. And this is a typical issue that we come up with radars. We really want good range resolution, so we widen our waveform and then we start interfering with adjacent channels. This is a real, while it doesn't cover all situations of radar optimization, it sure covers a lot of practical ones. And so what we did is we said, let's take a chirp, let's try to optimize jointly its bandwidth and its circuit, right? Its load impedance, its gamma L, real and imaginary, to try to get a real-time optimization. And let's do it in the case, what we're actually trying to do here is maximize bandwidth and meet requirements on the ACPR, the adjacent channel power. We're going back to ACPR, although we hope to implement this in spectral mask again, but we've kind of done our work where we work in ACPR first and then spectral mask. And we also are trying to optimize to stay within requirements on the power added efficiency. So in this case, we're constraining two of the parameters, the PAE and the ACPR. We're trying to get as much bandwidth as possible. Now my ACPR would be a constraint stay below this number, stay below this adjacent channel power. My PAE would be stay above this number, right? We need at least a certain level of efficiency. And then with those two constraints, I would try to get the optimal bandwidth possible. This is a diagram of what that optimization we expect would look like given our domain expertise of the situation. And I'll explain why this is. The adjacent channel power ratio is expected to, by the way, this is zero bandwidth. So we actually have negative bandwidth. So if positive bandwidth is an up chirp, then negative bandwidth is a down chirp. And in this case, we will just consider the upper part because up chirp and down chirp, it turns out we're testing very similar performance as you might expect. So as we go, if we have a very small bandwidth, then our adjacent channel power is going to be good for any impedance we choose. Because we aren't starting with a very big wide input signal, so we won't widen much for our output signal either. Now as we start increasing the bandwidth, as we increase the bandwidth of the waveform, now we're going to start having our third order intermodulation product spread into the adjacent channel. So we expect that fewer of the impedances shown in the Smith chart will provide us with an acceptable ACPR. So we expect our ACPR acceptable region to narrow in a cone-like way as we go up the Smith tube until we eventually get to a point where only one point is acceptable. So you see the tip just to the right of the red dot. That's the tip of the ACPR curve. Now the power added efficiency is expected not to change much with the bandwidth because we're measuring with a big broadband power sensor. So at least for the measurement we're taking, it doesn't matter what frequency the power is at, as long as we are delivering the same amount of power, we expect to get the same power and efficiency. We found that in reality with our experiments that we did on this device, it tended to widen slightly, but not much. So what we expect is we have to have a point that is inside the intersection of these two regions with as high V as possible, which means as high up as possible. So this, in this schematic, this would be our design solution. It's on the intersection of the two regions, and it's as high up as possible. So our goal is to find the highest point that is in all three of the surfaces, because that's the point of largest bandwidth by definition. So this kind of lends credence to our experiment slightly as we did an input bandwidth. As we changed the input bandwidth, we looked at for constant input power, what is the PAE measured on this axis. You can see the PAE was pretty constant. We went up slightly a little bit, but it stayed pretty constant. The ACPR really increased for fixed impedance.
Instead of using the absolute bandwidth, your analysis also consider using functional bandwidth. Is it the same?
Percent bandwidth could probably be used just as effectively.
Independent of this sensor frequency.
That could be done, absolutely. Although I think in this case, since we are considering, for a given optimization problem, we'd be looking at a specific center frequency, I don't think it would make a difference, but it's possible, yeah, if you wanted a more robust feeling for what you're doing, you could use percent bandwidth. I think it would lend you the same result.
Yeah, but in this case, for example, what was sensor frequency?
What was the center frequency? I believe we did their measurement test at 3.3 gigahertz. So, but we're not really, this could be applied in UHF or VHF or anything. These are system level techniques, and that's why I'm not focusing on frequencies or efficiency numbers or anything of that nature, just because they're really system level techniques you can apply in your own bench or in your own system. So what we did for our first paper, and we did the equivalent of a full load pole inside the Smith chart, or the Smith tube. So we had to do multiple load poles at different bandwidths. Look at all these bandwidths we measured. We did a full load pole each one of these bandwidths. Now I didn't do it. My two undergraduate students who just started in my lab did these load poles. They did it on a Saturday. Bob, how many movies did they go through?
About 14, I think.
They went through several, at least one solid length movie while they were running these measurements. And that was their indoctrination working in my lab. Those two students, by the way, just are graduating next week with their undergraduate degrees, and they just designed a reconfigurable amplifier.
Yeah.
So they did very good work in my lab. So they didn't do all boring stuff, but this was one of their first assignments. So anyway, the goal was to keep PAE greater than 7 for this amplifier and ACPR less than minus 27.5. And so these are just a smattering of load pole results, and this is viewing them as load poles, but you've got to think harder to do this than visualize them at once. So at 12.5, you can see that our joint acceptable region I've highlighted in yellow. So the ACPR limiting contour, this is the minus 27.5 dB C contour, which limits our ACPR. And this is our contour of the PAE limit, 7%. You can see that actually inside the PAE contour, we also get acceptable ACPR at this lower bandwidth. As the bandwidth gets higher, you notice that our PAE contour stays about the same, but our ACPR region gets smaller. So now we have this intersection region here that's acceptable. And as we get higher, now we have no intersection between the two, right? So we're probably going to be in this area, or somewhere between these two is where our optimum is going to be. Here is the view in the Smith tube of our actual measured data. So these are three-dimensional contours of the limiting ACPR and PAE points, which actually become closed surfaces. And you can see here we have a surface of minus 27.5 dBc ACPR. We have a surface with PAE of 7 greater than or equal to 7%. And this is the highest intersection point right here at the tube. Of the points we measured, we ended up at 13.75 megahertz, which is the largest bandwidth we can get out, and we have a reflection coefficient as shown. And that's our optimum point. And it provided a 7.5% PAE and minus 28.7, both close to the boundaries, but acceptable, and we got the maximum bandwidth out that we could while meeting our requirements. So this is a very applicable military type of situation that you would see, where you're operating a radar, and you have to change both the circuit and waveform parameters quickly. Quickly, right? That's the one thing I left out, right? Is quickly. I didn't show you quickly yet, did I? I showed you all day on a Saturday making measurements. That's not what we want for a load pole, right? For a radar, for a real-time radar. So, we worked on building the quickly unit, and that's illustrated in this publication. I don't know that it has come in press yet, but I think it's close. It's going through the pipeline. It's been accepted and seen going through that part. But here are the here's this fast Smith tube search. What we actually did was we did a two-step search. We started in the plane here, and we measured the optimum gamma. Then once we found the optimum gamma at a certain bandwidth, we did interval halving going up to try to figure out how we stayed at that same bandwidth, and we actually optimized the AC. Well, for our first step, we actually optimized the ACPR while coming within PAE constraints. That's the opposite of what we did before in our Smith chart search. But the reason we did that is because we the PAE is fairly bandwidth independent. It's like an elevator shaft. So what we wanted to do was get to the elevator shaft and ride the elevator shaft up as high as we could and still meet bandwidth requirements. So that's what we did, was we got to the edge of this elevator shaft, optimizing ACPR within PAE constraints, and then we went up using interval halving until we left the ACPR constraints. And then we could, if we want, reiterate again. That's step 2A and 2B. See we got here in step 1, which is 1A and 1B, and then we recentered ourselves and did it again. And this ended up being really good. Now, we're actually presenting a paper this week showing a direct search. It's in Wednesday's Spectrum issue session that Bob and I will be chairing. But we did a direct search, but it turns out that by using this domain expertise to do the two-step search, we actually used fewer measurements in most cases. So I'm showing you this one, but we will show you in Wednesday's paper both methods and how they compare. This is an over and up search. Notice that we use these, this is our search for gamma L. It's just backward from the search we did before. In this case, we fix PAE to maximize ACPR. That's our search in the plane. And then we do our search for bandwidth. What we do is we actually specify a bandwidth range. The user has to specify a range of bandwidths to be considered. And the first measurement is performed at the center of that range. So we do our first load optimization in the plane at the center of the bandwidth range that's specified. And then if we have an acceptable ACPR, we have the interval upward. So we start going up. If our optimized ACPR is unacceptable, we realize we're starting at too large of a bandwidth, and so we have the interval downward towards our lower part. And then the interval halving continues. We keep going down or up depending on whether we're acceptable until our half interval size goes below this parameter that we specified at the beginning of the search. So here's our measurement results. And we did 2 iterations just to show the improvement in number of measurements that could be added with the second iteration. So our first iteration, 1 over and up iteration, gave us 20 measurements, 21 measurements. For this one, at this starting point, so this is a 0.9 at 90, so this started up here with a fairly wide bandwidth range, 5 to 20 megahertz of our chart. This one started at 0 with a smaller bandwidth range, and here we have fewer measurements. But then we can take a second step, and you notice for the second step, this is looking from the top of the Smith tube down, we don't see much of a change here. Not much of a change at all on our gamma point, but we added 9 measurements. Now, how much bandwidth did we get? We got a little more bandwidth, we got 0.3 megahertz more, but the question is it worth the time to take those 8 measurements? And it might not be in some cases, so you have to determine that for your system, how many iterations to choose. We can't squeeze a little bit more out of it. Here we improved 0.25 megahertz. Then we improved, actually our PAE got slightly worse, but our bandwidth improved slightly, which is fine, right? We're not trying for best PAE, we're trying to get close to the 7% limit. But we required, once again, 5 more measurements. So is the time necessary to take those 5 measurements worth it? And that depends on what system you're using. We haven't gotten the reconfiguration times of these measurements yet because we were still implementing this on a load pull, mechanical load pull system on the bench. So we're counting measurements right now rather than measuring time. But this is going to depend on what technology you use, whether it's MEMS or reactor or whatever you end up using to do your reconfiguration. That will translate into a higher time, obviously. What was that? We haven't implemented this in an FPGA platform yet. No, this is on the bench. Actually, in our bench top, we control everything with MATLAB. We control the load pull with MATLAB. We control the waveform with MATLAB. So here's our measurement search results. You can see here for the single iteration, you can see we have different starting reflection coefficients and different bandwidths. And you can also see here are our end gamma L's, which are all very close. Here are our end ACPR and PAEs, which are close to 7%, minus 27.5. And here are our final chirp bandwidths. Notice we do get higher chirp bandwidths for a double iteration when we do 2 over and up procedures. And the number of measurements goes up too, right? So there's a cost we pay if you need more precision.
What I'm saying is that different ACPR thresholds at different frequencies.
Right, because those frequencies would be other users.
Different users.
Yeah, that's actually what we're using in trying to compute this dynamic spectral mass that Larry was talking about, was could you take a user over here, and if you knew his harmful interference level, could you translate that back to how much you're allowed to transmit? And same for user B, if he has a different harmful interference level and he's different location, can we translate that back at how much? And then we could create a dynamic spectral mass that we could optimize to with these techniques. So actually I think it's very coherent with that type of approach. And where you're thinking is exactly where we need to go. That's exactly what we need to do next. See, we have a hierarchy that has to be done here to enable this stuff, and Larry talked a lot about this. We have to be able to change how the system level thinking is done in terms of the regulation. So the regulation is done in real time and done on a from a pragmatic or a practical perspective rather than some fixed thing. And then these techniques will work very well in that type of upper level system hierarchy. This is the lower level techniques that will need to be used to facilitate that. Okay, well we have more tubes. We have another tube, the Power Smith tube. We talked about the bandwidth Smith tube. This is the Power Smith tube, and this was presented last month at WhamyCon in Cocoa, Florida. And my student Joe Barkay has done a lot of this work, and he presented these slides originally. So the Power Smith tube is another extension of the Smith chart, but this time the vertical axis is input power. Now this really hits at a circuit design element. So the bandwidth Smith tube is a joint circuit and waveform optimization. This is a circuit optimization, but if you think about it, input power level, or a lot of people talk about back off in the amplifier design, right? Because back off from compression may reduce efficiency, but it improves linearity. We already talked about that. So not only is the efficiency and linearity a function of of load impedance, but it's also a function of input power. And so the Smith tube is a visualization tool that allows us to jointly optimize the input power and reflection coefficient rather than having to go back and forth. Linearity and efficiency depend on them both, right? And so this allows three-dimensional plots. So I just want to think from a design perspective, and I presented this in WhamyCon. They have a lot of microwave traditional designers, and I think this can really influence how microwave designers design power amps, as well as to design reconfigurable radars. We did it for reconfigurable radars, but there's a lot of byproducts. So a typical amplifier designer, as he sits there in his cubicle, first he'd do a power sweep, right? He'd go to the bench or he'd go to a simulation and do a power sweep to find the best input power. Then he would do a load pull to find the best DML, right? So then he would say, okay, now I'm going to go from 50 ohms to DML, and I'm going to do another load pull, right? And he retunes the load impedance. And then you might do it as many times as you want, depending on how much time he has and how close he has to do this precision. I kind of think it's like throwing a how to swim book at a guy who's drowning. It can be ineffective sometimes to think in terms of this because you have to have a very educated person doing all this work, right? You have to be very smart about how you do these different simulations and when to run them. It becomes complicated. Now what the Power Smith tube allows you to do is it allows you to simplify your visualization tool and look at the design. Rather than having to go from Smith chart back to a power sweep curve, back to a Smith chart, now you can think about it as one picture in the Smith tube, and it could be better than holding a lemonade in the tube. You know, at least this is joy for microwave designers. So this allows us to simultaneously visualize, and that's the point. Is the Smith tube is a visualization. And we're going to show you how the design is done first, and then we're going to show you the quick optimization, which would be used in a reconfigurable radar transmitter or in a circuit design tool that will make things happen quickly, which ultimately the goal is to get good answers quickly, right? And so we'll show you how to get good answers first, and we'll show you how to do it quickly as we did before. So here's a simulation design example. We use a nonlinear FET model in an advanced design system, and we use a constraint of ACPR in this model of less than -40. And our goal is to select the input power and reflection coefficient to maximize the PAE while meeting this constraint. So So, well, by the way, we'll do this, and then I think we come to a breaking point, because Bob will go after that, so maybe we'll finish this part and take a break. Does that sound good to everyone? Take another brief break, and then Bob will come back. Okay, so then we have load pulse simulations of PAE and ACPR forming different values. Just like we did with the bandwidth tube, this time we're going to take load pulls at multiple input power values. So as you take at higher input power values, you expect to compress more, you expect better efficiency available to yourself, and worse ACPR. So let's see if this plays true here. These are some of the load pulls that we took. Here's an input power of 20 dBm. You see the yellow shaded region is the acceptable region for ACPR. Now let's back up a second. This is essentially the same optimization we did in the two-dimensional Smith chart. We're going to fix ACPR, assuming that we have a fixed adjacent channel power nutrients, and we're going to maximize the PAE. So the shaded region here is just, we're maximizing PAE under fixed ACPR, so the shaded region is acceptable ACPR. We're going to try to get the highest PAE possible in the acceptable region. Except now the regions are three-dimensional. So anyways, we increase the input power. We go up from 20 to 21 to 22. You can see as input power goes up, the acceptable linearity or acceptable ACPR region gets smaller and smaller. And eventually it will go away. We won't have any impedances that give us acceptable ACPR. What's interesting is the maximum efficiency actually occurs at 21, and you can still see we have acceptable region here. We're not going for the highest point, that was the bandwidth tube, right? We're just trying to find the maximum PAE. And what's interesting is as the efficiency, as the acceptable ACPR region decreases in size, it tends to recede away from the PAE optimum. So there is a clear trade-off here. You don't just want to get your highest power input and look for this highest power input where you have an acceptable region and try to maximize your efficiency, because that might not be a good load impedance close to the efficiency optimum. So we can see that the trade-off ends up lending itself the best over here. Okay? And if we visualize this in 3 dimensions, it looks like this inside the power Smith tube. So what we did here is what you would do, don't worry about this for now, you plot this ACPR 3-dimensional contour. It's really a surface now. This would be the minus 40 dBc 3-dimensional contour. And you can see, just as we expected, right, the points on the Smith chart that have acceptable ACPR recede as we go up because we're increasing input power, and so our adjacent channel power changes. Right, it gets worse, and so fewer points are acceptable. And what we did is we found the maximum PAE within those points. And this is it right here. And we actually plotted the PAE contour that corresponds to that point, and you notice that it's just touching at one location. So the way you would do this is plot the ACPR contour, find the best PAE point on that contour. We just plotted this PAE contour just to give you some reference. What's interesting is this also gives us some insight about how the system works. Do you notice that PAE seems to have a bigger representation? More points have acceptable PAE as we go higher. Mm-hmm. Right? The number of points that have 36.79 or greater is 0 here. And then as we go up, we get more points, then we start to have fewer points again. And this actually makes sense if you go all the way back. You're going to go all the way back. Don't tell me we're not being reconfigured. Too far back. We had an efficiency curve. That's it. You notice that this also gets wider. Look at what we're doing. We're looking at gain PAE versus input power. That's the red curve. As we go up, this is a fixed impedance though, right? So this is like fixing our point horizontally on the Smith tube and going up the tube. And you can see our PAE gets wider, or it gets larger, and then it gets smaller for a fixed point. And that would be like going up this tube. It's like going up this tube at this point, and we're going to have a higher PAE than a lower one, so we expect this to kind of be a little receding circle as we plot in 3 dimensions. And this actually makes a lot of sense based on what we would expect from the things that we pieced together. And we can design by this. So notice we've gotten a design out of this data. But it would take us a long time to make these measurements, right? More movies. Yeah. A lot more movies. Dr. Marks likes watching movies, but probably not this much.
No, not
yeah.
oh.
This is our load pole bench, by the way. This is our test setup. So you can see we have the tuner. We actually aren't using this tuner right now because we're just really varying the load impedance. So we have a Moore's microwave tuner, we have a power signal generator here, and we have a spectrum analyzer. And the tuners are controlled by Moore's software, which is, and this is our power meter, which is actually controlled by MATLAB. So MATLAB is running the whole show. And we want to put these on chip, and I have two students that have just designed a reconfigurable amplifier. The amplifier has some issues, but the reconfigurable load matching network is reactor-based and actually works. So we're going to be able to start trying to see how can we move this onto a prototype. This is where we've been validating and testing our algorithms. So what did we do for the measure? We did a measurement-based design doing the same approach. We took a measurement load pole, and here's the examples. I'll build it up in the same way. Here's some load poles at multiple input powers. You can see our acceptable region recedes. And here's our constrained optimum. This is the best PAE while having the ACPR less than our maximum, which was, in this case, minus 27.5 dBc on the same package device. And here's our picture of our ACPR contour, three-dimensional input power Smith tube. We didn't plot the PAE surface here. What's interesting is you can simulate a lot higher surfaces than you can measure, because as you go up this tube, you're using higher input power. We don't want to drive our device too hard or we'll blow it. So, especially if we're going to measure all the impedances on the chart. So I gave my students very careful specifications on how high they could push this device. So we show that here's our constrained optimum, same with design approach. And now comes the point where we try to do it quickly. And this is where the rubber is going to meet the road once again in optimizing in real-time reconfigurable radar. Or, this is great because this really is not a radar domain specific. It helps radar people, but just think about it. If you're working for microwave company A, and you're sitting there and you're working on something and you're saying, oh boy, I got to do all these simulations of load pole and input power and find the best condition. Instead of doing that, you could write a code to do this algorithm. You could sit down an undergraduate intern for the summer and say, here, punch these things in, and out is going to pop your answer. And we'll get it quickly with a small number of iterations. So, smart person, lots of time, versus not quite as knowledgeable of a person, punching in something to an algorithm and pressing go. So we think this has a lot of ways that it could make an impact on the CAD industry, as well as impact designers' lives around the country to be able to get to a design answer quickly with a simulation tool, as well as reconfigure a radar, which is our application here, obviously. So this is an intelligent algorithm, and it has these potential applications. So here are our full load poles, as I showed. This is our simulation search, and we actually can start this anywhere in the tube and get to the endpoint. Okay? And the reason I'm not showing you the guts of how this is done is because we're about to send it in. I'm literally one day away from sending it in for publication. So when the publication comes out, we will show you the guts of how this is performed. But it starts here and goes to the end with 33 measured points in this case. And it is a three-dimensional search, direct search. And you can see here, we got very close to what we got from the full load poles. Very close, actually even a better PAE value. Now, the fact that this PAE value is better, I don't believe is coincidental, because here we only have the resolution in the vertical dimension is based on how many load poles we want to measure. Do you want to go at 0.25 increments and spend 3 days watching movies, or 1 dBm increments and spend 1 day watching movies, right? So we had to make that decision, but in a direct search, you don't have to make that decision. You can set your resolution parameter, and it can vary in the vertical dimension just like it varies in the horizontal, which is a wonderful thing, and will save lots of time, I think, for designers. 33 measured points. You can't get even through the title slide of the movie that quickly. So anyway, these are the results. And here's our results in simulation from multiple starting points. Notice that we use several gamma L's, but also different input power values ranging from 0 to 25 dBm. So from the top to bottom of this tube that we look at. And look at our end gamma L's, very close. Our end input power is very close. Our end ACPR is also very close and near the limit of minus 40. Then we took it to the measurement bench. We found similar success there. Notice here that we had very close PAE, although we actually were below in this case. But you can see we used minus 27.5, and here's our endpoint. It looks very close on the Smith tube to what we got before. And there's the compilation of our measurement results. And you can see we vary between about 30 to 56 measurements here. So it can vary quite a bit in this case, but keep in mind you've added a dimension. So while you do suffer from the curse of dimensionality, if measurements are taken fairly quickly in your technology, 56 measurements may be a walk in the park to be able to get an adjustment made compared to having to scope out a full device. So this concludes our section on fast optimization techniques, and I want to kind of summarize what we've talked about. We've kind of gone from simple circuit optimizations to circuit and waveform optimization. And so these are measurement-based searches. They unfold as you make measurements, and you get better and better as you go forward. So this is really also very useful because if, for example, your system will fail at poor PAE, or the other case is maybe your regulator has placed ACPR requirements on you. You don't want to spend too much time outside of ACPR requirements or you get in trouble, right? So this actually gets you to the regions quickly. Well, it's an algorithm that unfolds. It takes you from wherever you start and improves your performance. The Smith tube is a very useful tool. We really believe that this will change how optimization is done because it provides a visualization and optimization space for the circuit and waveform parameters to be simultaneously optimized. And this next point is really interesting because it translates into what Bob is going to talk about after the break. But we missed one thing in our waveform optimization so far. Well, we hit on it in the bandwidth optimization. What did we talk about? Bandwidth allows us to do better range detection, right? Which is a common application of radars. But it's funny because when I first started doing this work, I had my graduate student, Matt Moldover, in the lab. I probably should have changed the names to protect the innocent. But he was taking my colleague's avionics course. And my colleague came in and told me a story of what had happened in his class because Matt had been hearing all these things about spectral requirements from radar from me, and he'd been working on my projects, and we've got to make these radars spectrally compliant, get them below the spectral mask. And so the professor next door came into my office and he said, yeah, I have Matt in my class. He said, I asked the other day, what is a radar system supposed to do? What's the purpose of a radar? And Matt said, stay within spectral requirements. So apparently I'd been hitting that home, and I think this is the point here. We've done a lot of talk about that. But what does the radar really do? It detects range and Doppler. And amidst all the clamor that we have had to go through to try and get radars to operate spectrally compliant, we must do these optimizations to optimize the ultimate goal of the radar, which is to detect range and Doppler in a target, according to a set of predefined parameters. And this is why we need to pay attention to the ambiguity function. The bandwidth parameter obviously gives us an ambiguity function if we maximize bandwidth. It gives us very good ambiguity, very low ambiguity in the range dimension, and poor ambiguity in the Doppler dimension. And what we're going to do now, and what our research is presently focused towards, is how do we optimize waveforms to meet spectral mask requirements while giving us good ambiguity properties. And then overall, how do we optimize the entire circuit and waveform together to A, give good ambiguity properties of its output waveform, which there is influence on that, and we'll show that by the circuit. B, meet spectral mask criteria, and C, be as power efficient as possible in this joint. So we've got a platform for joint circuit and waveform optimization. I would say let's take about a 5 to 10 minute break, and we'll come back. And Bob will talk a little bit about ambiguity function optimization from just a waveform perspective, and then he's also going to bring in the spectral mask. Actually, Bob has an interesting tutorial on what is the ambiguity function. So we're going to go back and examine that from very first parameters of what it is, what it does, talk about some common myths with the ambiguity function, and then talk about how to optimize it with the spectral mask, and then I'll come back at the end and we'll discuss how the circuit affects the ambiguity function. And then we can conclude with a little bit of discussion and some questions as to how the work might move forward and what we can do to continue to advance it. So anyway, let's take about a 5 minute break and we'll reconvene. Thank you. All right, Bob, I think we're all here, so.
Okay, I think it's kind of where we're at. We've been out for kind of the trees, but we occasionally, as Dr. Bill said, we have step back and have to look at the entire forest. Okay, the entire forest is as follows. The future of communications and radar is going to require adaptive and reconfigurable systems. We're going to have to be able to switch bandwidths. We're going to have to be able to switch operating points. And in order to do that, we need to optimize the waveforms. And we've seen the waveforms being optimized in places such as waveform diversity and cognitive radar, cognitive radar, and cognitive communications. However, that isn't enough, because once you change a configuration, once you change your spectrum, or your operating frequency or such, you're also going to have to be able to reconfigure your amplifier. Because the hardware, in addition to the software, needs to be reconfigured and adapted, and it has to be done at the same time if we're going to have the flexibility. Gone are the days when a transmitter is doing one thing all the time. And so we have to have this reconfigurability on the fly. Now, Charlie Bayless has spent some time speaking largely about the adaptation of the amplifier. That's the stuff in the front end. There also needs to be some things at the back end, and eventually the two need to be married in order to get a good, effective system for the future. So I want to talk about some of the back end sort of stuff and the signal synthesis. We have signal synthesis for a number of different reasons. One is the ambiguity function, the classic determination of the range and the Doppler of the target. We have other applications, correlation applications. You were talking about the idea of looking at pattern recognition in terms of radar, which is largely correlation sort of operations. So all of those need to be done, and again, the signals have to be synthesized both with the idea of the signals and the hardware being done at the same time. So I'm going to go back and revisit a very familiar area of signal generation on the back end, which is the ambiguity function. So let's talk about the ambiguity function, and in going back and reviewing this and coming up with some of the different reviewing the different literature that we have for the ambiguity function, it turns out that there's a lot of misinformation, and there's some misrepresentations. So I wanted to go back and just look at the ambiguity function from basics and then take it up to the point where we are going to incorporate it as a radar signal. The ambiguity function actually has its basis, its foundation in the area of matched filters. The idea is you have a bank of signals here, and you have an input signal, which is here, and you want to find out which one of these signals is closest, in some sense, to this one. And the way you do that is you minimize the difference between the two signals, but if all of the elements in this have the same energy and you expand them out, it turns out that minimizing this is the same as maximizing this in a product. And the reason is because this and this are going to be common to all of the terms. So in terms of the minimization or the maximization of this, these two terms don't matter. And the only term you want to play around with is minimization of this term. This turns out to be the inner product. And so we want to find the minimum of this signal plus this signal. We assume that all the elements within the library have the same energy. And so these terms are the same, so we just have to minimize this. And this is actually what we want to announce as our signal as we begin to compare the input signal with all of the signals that are received. Now the thing is that we don't have to place these signals separately in a filter bank. We can actually place them side by side on a time series. And the entire idea then is to take this signal, run it across, and then you figure out where the peaks are. And that's the classic correlation sort of interval. And you can see the math of this up here. And so here's a simple example. We have some noise on the top. We have a pulse, and right here is the signal plus the pulse, and the signal totally buries the pulse. If we perform a correlation, that is, we take this and we slide it across during the correlation, we get all of this garbage, and now it peaks up exactly at the location of the pulse. Classic correlation. So here's a pulse train. We have noise up here. We have the pulse train. We have the signal plus the noise. The signal is totally obfuscated by the noise, except that when we come out and do the correlation, we get peaks to where the locations of the ones and minus ones are. Now notice something interesting, and this is very interesting, is that all of these peaks are triangular in shape. Why are they triangular in shape? Because the autocorrelation of a rectangle with itself is a triangle, right? And if we were to choose different shapes, if we were to choose a shape other than a rectangle, we would get a different correlation flavor, right? If we were to use like a triangle, we would get something which would be closer to kind of Gaussian, I suppose. So the shape of the pulses determines what the results are. This is, in fact, exactly like the ambiguity function. And we'll see that the choice of the pulses up here in this triangle as an artifact of that choice is much like the ambiguity function. Here is the actual, here's on the top here is the actual correlated signal, and these are the pulses which we get. And again, the reason that we get the triangles is because the correlation of a signal with itself is an ambiguity function. Now there are a classic set of codes called Barker codes, and the Barker codes are known for having really, really good correlation. In fact, they're the optimal. They're the best you can possibly do. And here are a number of the different Barker codes that we have. And it turns out that only number 13 exists. The Barker codes are actually used in IEEE standards for communication. It's a standard way of communicating. And here's an example of Barker codes. What happens is that using the same sequence of ones and zeros that we used before, we use a plus Barker code here and a minus Barker code over here. A plus one, I guess we have another plus one, and then we have a minus one. Notice that the thing is negative here. And if we correlate this with the Barker code, we get this beautiful clean signal out here, which not only identifies the location, but also the amplitude of the transmitted signal. On the bottom here, we have the Barker code in the presence of the noise. We perform the correlation of the Barker code with itself, and we get a beautiful result that we have here. So the Barker code, in terms of communication, a very temporal system, has optimality properties, as long as your sequence is upwards of 13. However, Barker codes are good codes. And we're going to talk about ambiguity functions where you have good signals and bad signals. Well, you also have good signals for Barker codes, but you also have bad signals. Up here, let's see, for example, this is the Barker code that we just saw. And we have the Barker code here. And so we repeat the Barker code 1, 1, and then multiply it by -1, 1, 1, and this is the corresponding result. We can also be very stupid in the choice of our code. We could choose something like as you see here, a 1, -1, 1, -1, 1. And if we use that as our code instead of the Barker code, we would get this garbage out here. Now you notice that for the Barker code, we are very distinct in the choice of where we decode the location of the result. Down here, the red denotes where the pulse should be, and the blue denotes the correlation, and you can see there's lots of ambiguity in terms of where to choose it. And the reason is that we've chosen the wrong curve. Now it turns out for temporal signals that you do have the best and you have the worst down here, and the best is the best and the worst is the worst. For ambiguity, when you're looking at the trade-off between Doppler and range, there isn't an obvious best, there isn't an obvious worst. You have a trade-off between the range and the Doppler that you have to choose. So here's what happens. This is the beginning of the derivation of the ambiguity function. We have a baseband signal, and the baseband signal is given by the in-phase and the quadrature terms. This is the RF circuitry that actually takes the baseband signal, heterodynes it up into an RF signal. And that is given by the real part of G of t, which is the baseband signal, times e to the j, 2 pi to the t. Many times in the text, they get very good, I find it confusing. They don't put the real part here, and they actually talk about generating complex signals. Complex signals don't exist, right? Because you have an imaginary part, and imaginary parts are called imaginary because imaginary doesn't exist. So therefore, we need to just talk about the real part of it here. So the entire idea of ambiguity, of course, is that there's a transmitter, it transmits a pulse, and you get a reflection. Now the pulse, the signal that's transmitted is g of t times the cosine, and w is the signal. Now g of t, turns out, is going to define this ambiguity function and the ambiguity of your result, much like we use the rectangle or the Barker code. That's going to determine the ambiguity of the receipt. Now when we get it back, what are we going to get? We get back this exact signal, except that it has a little Doppler shift and a little time shift associated with it. And these are unknown, and our job is to define what, find what this Doppler shift and what this other shift is, because it's going to tell us the speed of the object, and of course, delta t is going to tell us the range of the result. So what we're going to do is we're going to take this entire signal, and we are going to, instead of a matched filter bank with finite numbers, we're going to go to a matched bank that has an infinite number of numbers corresponding to all different values of W, delta W, and all different values of W, delta T. And it turns out it's the same as the matched filter, and minimization of the mean square error between the received signal and W and nu is our search variable. So we are maximizing or minimizing over all W's and all nu's. And it turns out that it's the same as the matched filter, and minimizing this is the same as maximizing this expression here, if you just go through the mathematics of it. And in here, there's this funny function called the ambiguity function. And this is where the ambiguity function comes from, and again, it's just like the correlation of the rectangle or the Barker codes, if you will. So at the bottom of here, we have one of the definitions of the ambiguity function, and this is, again, what we would like to maximize. Now, the interesting thing is that notice that we actually want to maximize the real part of this product. In most of the places that you see, most of the radar text, they say, no, you don't, you want to maximize the magnitude. No, we want to maximize the real part. But it turns out that in many cases, it actually doesn't matter. Because here you have the actual envelope, and we want to maximize the real part of this. Now, maximizing the real part of it means that we want to maximize where this biggest peak is at. But that means we would have to figure out the values of all of these different peaks and figure out the maximum value. That takes too long. So something we can do instead is just look at the envelope of the peak, recognizing this is an RF frequency, it's oscillating really crazily, and we can actually say that, you know, maximizing the peak here is kind of the same thing as maximizing what the envelope is. And the difference is going to be very, very small. So that's the reason most of the text talk about maximizing the magnitude as opposed to the actual real part. So the result that we get is like this. We receive this signal, and we do a matched filter on all of the different possibilities for all different values of tau, all different frequencies u, and we are going to get a peak, a correlation peak, to where the actual true delay in Doppler frequency occurs. And the cool part of it about it is that like the other correlation, that if the maximum value is here, if we change, the maximum value is here, that the shape around each of these extrema is going to be exactly the same. In other words, it doesn't matter what the Doppler shift is, it doesn't matter what the delay is, the shape of that function is going to be exactly the same, and that is the ambiguity function. And that's the reason that we can shift it to the origin and study it. And that's what happened, that's the definition of the ambiguity function. This function shifted to the origin, where we can study some of its properties. So one of the myths we just showed was that it's not the magnitude of the ambiguity function you want to look at, it's actually the real part. Another myth is that the ambiguity function is uniquely defined, and even Woodward, in his original papers on the narrowband ambiguity function, gave different definitions of the ambiguity function. Here's Skolnick's definition, and up here is the way that we defined it. So you find actually a number of different representations of the ambiguity function. The cool part is that if you're dealing with real signals, all of the ambiguity functions that we have defined are defined exactly the same. They have the same magnitudes, I should say. So in terms of just finding the magnitude, that's okay. The other myth that you have about the ambiguity functions is that the ambiguity function of the baseband signal is the same as the ambiguity function of the RF signal. They're not equal to each other, even though some books kind of allude to that. And I think in practice, a lot of people find the ambiguity function of the baseband signal because it's easier to do. And but the actual ambiguity function is, it's the baseband, but it has an RF frequency modulation in here, and it also has some very high terms. Fortunately, these high frequency terms are outside of the range where we really care anymore. So this is another one of the myths. The other one is that the ambiguity function is not invertible. Here is a quote from all of these. I can support my quotes, but this is by Lebanon. It's one of the great radar engineers. He said, "No analytic methods for existing a signal given its ambiguity function." In other words, you can't invert the ambiguity function. And in terms of signal synthesis, this turns out to be very important. If you take the ambiguity function and you generate the marginals by summing all of the rows, you actually can show that you get the original signal back. So it is invertible, at least within a scaling constant. So you can invert the ambiguity function and you can get back the correct results. I'll skip that one. So now with that background, let me show you how we can synthesize an ambiguity function. This would fall under the, I guess, under the topic of waveform diversity. Given a specific target scenario, what signal should you generate to give an ambiguity function with certain desired properties? And I'm going to talk about a whack-a-mole. Anybody play whack-a-mole? Whack-a-mole. You play whack-a-mole? Okay, yeah, that's good. Little mole comes up, you whack it, and huh?
With my son.
With your son, you play whack-a-mole. Okay, so we're gonna talk about whack-a-mole. One of the things that's a common thread in all of this is some of the things that Charlie Bayless talked about, and some of the things I want to talk about, is fundamental to this new era of shared spectrum and flexibility in going from different spectra is adaptation. Adaptation, in its essence, is machine intelligence. In fact, some of it is elementary machine intelligence. In the 1990s, there was a paper published called the No Free Lunch Theorem. The No Free Lunch Theorem says that one adaptation or one search algorithm works better than any other algorithm in the absence of knowledge of the problem you're solving. Another interpretation is that to solve an adaptation problem, you have to impose into that problem as much domain expertise as you possibly can. And what Dr. Bayless showed, for example, there was adaptation, there were a number of elements of domain expertise. One was incorporation of something called Zada convexity, where we assumed that, and the domain expertise bore us out, that many of these contours were actually convex. If you look at the contours, they were all convex contours. That's a domain expertise that we can apply towards the adaptation of the hardware. In a similar fashion, we need domain expertise in the generation, in the synthesis of signals at the back end. So we need them in both places, and they have to be intelligent. You just can't throw steepest descent optimization of one of these and expect it to work all the time. The more information, the more domain expertise you can incorporate, the better you're going to get. I'm going to show you a technique which is very nice and very general in terms of meeting a number of different constraints. We talked about the spectral constraints. We're also going to talk about constraints associated with the ambiguity function. And it is like whack-a-mole. So I'm going to talk first of all about convex sets. A convex set basically is if you have a set of points, I'm going to talk about sets of points here, and you have any 2 points in the set, if you connect them with a line, it turns out that all of the elements of a line connecting any 2 points of the set are totally subsumed within the set. So no matter what 2 points I chose here and here, whoop, this line is totally within the set. If I chose the points up here and down here, whoop, that line would be totally in the set. And that has to occur for all values of, all choices of those 2 points. Here are some convex sets. I forgot to take the animation out, that's okay. And here's some sets which are not convex. This is not convex set of points because I can choose 2 points here, connect a line, and it's external to the set. Now, why is this interesting to us as engineers? It's interesting because many signals, many common classes of signals form convex sets. Let's take, for example, the set of signals which exists between a lower limit and an upper limit. That's a set of bounded signals, right? And we would like to, you can see where we want to limit peak powers, instantaneous peak powers, where we would want to use something of this sort. Well, it turns out the set of all signals that are between a lower and an upper level are indeed a convex set in a Hilbert space. In fact, the convex set turns out to be a box in a higher dimensional set. Okay? Here's another one, band-limited signals. All signals that are band-limited that have a 0 component in frequency for a frequency above some sort of bandwidth. That is also a convex set. And it turns out to be a convex set, which is a plane in higher dimensions. A plane happens to be a convex set because if you choose any 2 points in the plane and connect the 2 points, that's going to stay in the plane. So the set of all band-limited signals is also a convex set. Signals with bounded energy. Say you want a signal that has an energy less than 6 joules. You can also bound that energy. It turns out to be a convex set. It turns out to be a hypersphere. And of course, if you have a sphere, any 2 points that you choose you're going to have points connected. So you can see these and many other signal sets, which I'm not going to present, form convex sets and are very useful. So what? We have convex sets, we have signals which are convex sets. Now comes the interesting synthesis part. Okay, I'm not going to show that. It turns out that for every convex set that you have, if you have a signal external to the convex set, there is a point uniquely closest to this in the mean square of sets. So here, it turns out that that's the closest point. Going from here to here is referred to as the projection onto the convex set. And we're going to use this concept of alternating projections to synthesize signals. Now, if we choose another point, if we choose a point over here, it's going to have a different projection because if you choose different points. And if you choose a point that's in the set, well, then when you project, you stay exactly where you are because you're already in the constraints. So how do we do projections onto convex sets given these signal classes? I'm just going to give the 3 examples here and then we'll move to larger ones. Say you have a signal which is not bounded. In other words, it doesn't go between a lower and an upper limit. You want to find the element in the set that's closest to this. It's very intuitive, and it turns out the correct answer to say the way that you project onto this convex set is you simply clip off the top and the bottom. That turns out to be the projection onto that box, onto that convex set. And here's the idea of projecting onto the convex set. What about a signal that isn't band limited? Suppose you have a signal that isn't band limited and you want to project it onto the set of all band limited signals. How do you do that? You run it through a low pass filter. It makes all the sense in the world, right? So that's exactly what we do. We take the signal, we run it through a low pass filter. That turns out to be the projection onto that convex set. So all of these signals, the ones I've mentioned here and the ones I don't have time to mention, are all intuitive. They're things which are used extensively in signal analysis and signal processing, and they all have very simple intuitive projections. If you have a signal that has too much energy, what do? You just multiply it, you just amplify it by, de-amplify it, I should say, by some value to give it the maximum value of the energy. And all of these have that sort of thing. Now, all of that's good. We have convex sets and we have projections onto convex sets. Here's the verb. If you perform, well, if you have the intersection of two convex sets, that intersection is also convex. Okay? So here we have a kind of an ellipsoid intersecting with a line. You can see this little line segment turns out to be a convex set. So any of the intersections is kind of cool. And here is the verb. If we take two convex sets and we project back and forth, this is the whack-a-mole. If we project back and forth, we always will go to a point of the intersection of the two convex sets. Let me show you what I mean. If we start here, project onto C2, C1, C2, C1. You see what's happening? It is generating a fixed point. It is approaching this point and will eventually converge to a point which satisfies both of the constraints. And we can think of these convex sets as constraint sets. And we want to generate constrained waveforms. If we start at a different place, over here, we might go to a different point in the intersection, but we always get a point which satisfies the constraints. But the cool part is if you have three convex sets, for example, and they only intersect in a single point, no matter how you project, it's always going to end up at that single intersection. You can start out here, and go boom, 3, 4, 5, and you can see you're going to go towards that point. If you start out at the bottom right here, and you do the projections, you are also going to end up exactly at that same point. So no matter where you start, you're going to end up at the same point. Now, how can we apply this, for example, to synthesizing radar signals? I'm going to talk specifically about the case of synthesizing a radar signal that has certain ambiguity function properties, that meets certain ambiguity constraints, and those constraints can always be thought of as existing within a set. So, here we have the ambiguity function. Remember I said that the ambiguity function could be inverted if we added all of the columns, we could get the original signal. Well, guess what? If we add all of the rows, we get the spectrum of the signal. So we have both the spectrum in the ambiguity function. This is the t-tau plane. This is the ambiguity function plane. We both have the original signal and we have the spectrum, which we can get, if you will, from marginals. Much like marginal probability density functions, you know, where you integrate along rows and columns. So here's the problem. We want to synthesize an ambiguity function that detects a target, but out here we would like to avoid any sort of ambiguity in these areas. So we want to detect this problem, and we want to avoid ambiguities in this area. For whatever reason, we might know that there's targets in that area, for example. How do we do that? Well, here's the idea. All functions are not ambiguity functions. All functions are not ambiguity functions. So we're going to start with an ambiguity function, and then let's suppose we want to synthesize an ambiguity function which is 0 within this blue box. Okay? That's our constraint. So we want to synthesize an ambiguity function which is 0 within this block. So what we do is, this is whack-a-mole. We go whack, whatever this is, we're going to set it 0 to be 0 within the side of this block. The problem is once that's done, this is no longer an ambiguity function. We've destroyed the ambiguity function nature of the problem. So now we go whack, and we make it back into an ambiguity function. How do we do that? Well, we take the projection here, we take the projection here. These are two different estimates of the underlying signal. If it were a true ambiguity function, these two signals would be Fourier transforms of each other. But they're not, so what we do is we actually take the two marginals here, this should be the spectrum, this should be the Y, then we combine them into a single signal, that's hard to say, a single signal down here, x of t, which is, for example, the average of the two. Then we take this signal and we go back to the top and we make an ambiguity function. So again, this whack-a-mole. Boom, it satisfies this constraint. Whack number 2 is an ambiguity function. Then we whack it again, and we are projecting back and forth between these constraints in order to get a nice result. Here is the result of doing that, of going through this synthesis result. And you can see that since we require this to be 0, that we get a nice value of 0 around here. And here are the actual signals which were synthesized for the radar that gave these ambiguity function results. Here's another one. Suppose that we wanted it 0 within the purple here. This is the result of the alternating projection results, and you can see it works very well. So this is something, again, which can be added to the back end in order to synthesize ambiguity functions. Here is a cool result. Suppose that we wanted all of the ambiguity to lie on this line. And we applied this whack-a-mole POCS, alternating projection. Without even telling the function what to do, the POCS, the alternating projection, actually generated a chirp as the result. We know already that if we had a chirp, that it would be along this line. This is the result of the alternating projections that we were able to use, and the signal that was generated turned out to be a chirp, which was kind of cool because we didn't tell it at any point that it wanted to be a chirp. Yet the signal synthesis was able to do that. So it was kind of a sanity check where we were able to get the results very nicely. So, one of the cool things about the alternating projections is that if you want to add conditional constraints, right now we're just saying, whack, it's an ambiguity function. Whack, it obeys the constraints. It's 0 within this area. Whack, it's an ambiguity function. There's nothing which prohibits us from adding an additional constraint, right? So we have 3 modes to whack. And that's one of the nice things about this approach is that you can add or take away any of these different constraints. Here is an example. Charlie Bayless mentioned about it. Remember we had the spectral constraint that we had to satisfy the spectral mask. So we're going to add in a 3rd mode to whack. It's got to be an ambiguity function that has to meet these certain constraints. In this case, we took the highest ambiguity along a line, and then the 3rd thing is that it had to meet the spectral constraints. So we go whack, 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 and then we get to the end. The first mole pops up again, so we go back and whack it, and by repeatedly doing that, we ended up with this very nice ambiguity function here, the ambiguity function here. And we noticed, it was kind of interesting, notice the spectral mask is kind of like a low-pass filter or a band-pass filter. That's exactly what this came up with. It took that big, long result and spectrally limited it to a finite bandwidth. And the whack-a-mole constraint did that very nicely. Here is the signal which was generated, which was a nice chirp, but it was a tapered chirp. It was a chirp that delayed at time, and that delay kept the ambiguity function from turning off and turning on and giving us this high frequency components. So we were actually able to get rid of it. So you can see here that this is potentially a powerful kind of way to do things. So the extension is application to other synthesis of other radar signals. I think that if one had, for example, the correlation sort of thing where you wanted to begin to do pattern recognition on the return signal, that you could also synthesize signals very nicely for this. Convex set dilation, I'm not going to get into that. This is a technique that we can apply when the convex sets don't intersect. And here's what we would like to do. Notice we have had a little iteration, but this has been iteration on the back end. It's been on the signal synthesis. Getting back and looking at the forest again. We've had a little back end iteration on the ambiguity function. Dr. Bayless has mentioned all of this reconfiguration. This is on the front. Eventually what we need to do is we need to do both of these in concert. One of our students just came up with some results wherein there was hardware in the loop, but the hardware itself was not reconfigured. So in other words, if you have hardware operating at a specific operating point, you can actually perform this optimization with the hardware in the loop, but not be assured that the hardware is configured to the optimal transmission. And what we need to do eventually is to have both of these happen at the same time. And I think you mentioned how we're going to do it. I think this is the approach that needs to be done, is to do both the signal synthesis and the hardware reconfigurability, adapting at the same time, using lots of domain expertise. You can't just do it by throwing an adaptive algorithm at it. It has to be with some forethought.
Bob, something I might bring up here is it's interesting to note that all this work here is experimental based, or is based, it has no cause and effect linkage to making the algorithm work, which means that you can put hardware in the loop, you can do anything, and it does not change the result. There's no analytics involved in taking these from cause to result.
Okay.
Does that make sense? So basically, you try something, you whack the mole, you see what you get, but you don't go for, there's no linkage in the algorithm from whacking the mole to what you get. So as a result, you can put hardware in the loop, you can do anything. You look at your output and you go around and whack the moles until you get something that corresponds.
And it could be that you whack-a-mole in the signal synthesis and then you whack-a-mole in the reconfiguration.
Right.
Yeah.
But the point I'm making is you can stick the amplifier in the loop here and have no problems. As we'll see in a little bit, it does change the ambiguity functions, but there's no cause and effect in this algorithm anyway. So it's perfectly great. It works. It sets itself up to work really well in that type of situation.
Yes.
You think?
And I think that concludes. I finished early, so I'll turn it back over to Dr. Davis.
Do you all have any questions?
Oh, do you have any questions for me?
Yes, questions.
I covered a lot of material here, I know. If you're interested in POCS, I don't know if I referenced it here.
No, that's what I was checking to see if you got it.
Okay. Write this down.
I'm ready.
Handbook of Fourier Analysis. By me, Robert J. Marks, Oxford University Press, Chapter 11 is all on POCS.
Okay, thanks very much.
Thank you. Okay.
In concert with this description of the ambiguity function, one of the things that our student Dylan Eustace did And Dylan has worked with Bob heavily on a lot of this ambiguity function optimization. And one of the things Dylan did, actually before he worked on a lot of this, was he was working with Bob and I on what does the amplifier do to the ambiguity function. So you can see we're kind of approaching this problem from all sides. We're sizing up this big beast before we totally go in and tear it apart. And that's kind of how we're attacking this. And we want to see what does it do to the ambiguity function. Now, as I mentioned, this should be, actually Dylan is working on results right now that show the amplifier value. So the ambiguity function, as Dr. Marks mentioned, describes the correlator output relative delay in Doppler to the desired target. And power amplifiers, how do they affect the ambiguity function? Well, if the ambiguity function is a correlation, which we learned that it is, then if the time domain waveform is affected, we would expect the correlation to be affected as well. Furthermore, if the spectrum is affected, we expect the correlation of the spectrum to be affected. Now, the time and range axes of the ambiguity function plane are the correlations. I don't know, I think that was in your slides somewhere, but those are the correlations in time and frequency. The time axis of the ambiguity function is a temporal correlation, and the Doppler axis is the frequency correlation. So, if the spectrum is affected by nonlinearities, i.e. spectrum widening, we would expect that the frequency axis, the Doppler axis, which is the frequency correlation, we expect. If the time is affected, we expect the temporal axis to be affected. So therefore, we do have a hypothesis that we should see some changes on the ambiguity function based on the types of nonlinearities that we encounter in amplifiers. And that's what I showed here. I just repeated that these are correlations. The tau axis is the time autocorrelation of the waveform, and the frequency U axis, which is Doppler, we used U to represent Doppler here, is the frequency autocorrelation of the waveform. And those can be derived by inserting U for U equals 0 up here, which is the tau axis, and inserting tau equals 0 down here, which is the U axis. So there's a lot of, there's some literature on what the ambiguity function does to distort, or how the ambiguity function is distorted by the amplifier. Most of the work that I've seen that's really good has been done by Professor Shannon Blood at the University of Kansas. He's done some really good work on amplifier in the loop. And a lot of his results look at zero range or zero Doppler cuts of the ambiguity function, which is a lot of where the interest is as well. And one of the things that's concluded by the literature in general is that transmitter nonlinearities cause widened range side lobes or increased range side lobes. It does affect the range side lobes of the device. And optimization, which has been done in many cases, can decrease these range side lobes. That's what's shown in the literature. Well, we wanted to do a little bit of very simplistic work on this. As I mentioned, being a student not too long ago myself, and always being a student, I try to go back to the very basics when I'm learning a new concept, and this is not a new concept for me, so I want to go back to the basics. So, what happens if we have an amplifier and we run it into saturation? We do a simple experiment. We take a sinusoid in, we run that sinusoid, we increase the power, and we run the amplifier into distortion, we're going to end up approaching a square wave. So what if we looked at comparing the autocorrelations of a sine and square wave? When we autocorrelate a sine with itself, we expect to get a sine out. When we autocorrelate a square wave with itself, we expect a triangle. When you do an ambiguity function, usually ambiguity functions are compared by normalizing to their energies. And the energy of an ambiguity function actually is the center. The 0, 0 point of the ambiguity function represents its energy. It's been shown that that's the case. So that would be the point at 0. If we look along the tau axis here, the range axis, the point at 0 should be the same height for both. We should recenter the waveform. So in that case, you can see that it turns out the square wave actually fits slightly inside here. The triangle from the square wave fits slightly inside the sine wave from the sinusoidal autocorrelation. But they're fairly similar. Now, if we look at a sine wave versus a square wave, and we look at just the spectrum, we didn't actually do the correlations here, there's a lot of data involved in this. But if you look at the spectrum, it should be apparent what's going to happen when we do the correlation. The red lines are the non-distorted spectrum. But what if we have nonlinearity? What's that do? It creates harmonics. waveform. So if I have a square wave spectrum, I'm going to have harmonics. And so those harmonics, this is the 0 point, so I have harmonics here in the square wave. And when I correlate this, if I correlate the square wave with itself, I'm going to have additional terms that show up out here that don't show up in a correlation of the red signal spectrum. So that would be my u-axis. So when I have additional terms on the u-axis, I expect additional terms in the correlation, additional terms on the frequency axis of the ambiguity function. So Dylan went to the simulator. He went to the simulator and we talked about doing an experiment where we ran a 7-pulse Barker code through a nonlinear FET model using the Advanced Design System, which is our microwave simulation package. We use a nonlinear field effect transistor model. We ran the saturation with a 7-pulse Barker code in a time domain simulation. We looked at what happened to the output time domain waveform. And then we took the time domain waveform and put it in MATLAB and performed the ambiguity function operation on both the input and output. So we drove the amplifier very high so that the signal at the output would saturate significantly. So here is the results of the simulation experiment. Here's our input Barker code. It's a 7-pulse Barker code. Here's our amplifier. Here's our output. So if you look at our output waveform, you can see the tops are much more rounded or flat. The peaks are much more distinct here. And the spectra, what's interesting about the spectra, and there's actually backing for this. I was scratching my head trying to figure out why did this happen. Well, let's talk about what we see first. What we see here is one main lobe. What we see here are multiple lobes on the output. But you can see that the higher spectral content does extend wider out through those multiple lobes, even though the main lobe is a bit narrower. Now, if you actually look at this, these look very similar to triangle waves. What is the Fourier transform of a triangle? Anyone want to venture a guess? I just taught communications, so we dealt a lot with this with line coding and stuff, so I'm really fresh on this. But triangle? You know, Dr. Marks, what is it?
Sinc squared.
It's a sinc squared, right? What is the, and I believe, I wrote this down, I believe it's half the bandwidth of its corresponding rectangle. You have to go to your book to check it out.
I would.
But the output is closer to square wave.
Yeah.
What's the Fourier transform
Right.
of square
So
wave?
it'll be half the bandwidth because it's like you're multiplying two square wave.
I think the sinc squared is half the bandwidth.
W over 2 to plus 2 over 2.
So my point is, yeah, we have a sinc here, then we'll get a sinc here, we'll get a sinc squared here, but the sinc ends up, no, actually the sinc, it looks like, I found out why this, and it did work. I remember I did these calculations on the plane. And this main lobe ends up being half the bandwidth of this. This is a sinc squared, so its second, third, and fourth lobes, which are very small, end up getting smaller. And this is a narrower band sinc, and its other additional lobes are still visible. So this actually makes really, really good sense when compared with the theory, why this happens. But this does end up spreading, as we would expect, from these flatter pulses. We see spectral spreading, but we do see more of these lobes because we have a narrower bandwidth sinc function. So anyway, that's what happens to the. This is just the time and frequency domain. That makes sense. We get what we'd expect. What happens to the zero Doppler ambiguity function cut, which means that we are on the range axis. So that would be performed by doing a correlation at the input of this waveform with itself, and at the output we're doing an autocorrelation of this one with itself. So we'd expect, we see the locations of the input and output similar, and we get slightly flatter pulses possibly for the output, but we can see this better on a heat map, which I'll show in a second. We can see the results a little bit better of the widening of the pulses, which we'd expect from a square versus a triangle. I wanted to show the zero range plot in here, and I thought I had done it, but apparently it's not here in this slideshow. So, but if you come, we're actually presenting this as a paper. This work is a paper that we're presenting here on Wednesday in the Spectral, I think it's Spectrum Issues and Challenges session with our Smith Tube latest results as well. We'll be presenting it, and we'll have the other slide in it. But the zero range ambiguity function also shows widening of the spectrum. As we saw widening of the spectrum, we see that as well in the zero range ambiguity function, which is the autocorrelation of the Doppler dimension. But the heat map contains the same results. This shows it all together. This is the entire ambiguity function at the input and output. Red being higher and blue being very cold or low. So at the input you can see here in the range dimension, we have these little narrow points of high value. And they extend in the Doppler, these ridges extend in the Doppler dimension, but they get cooler in the Doppler dimension pretty quickly. Which then indicates that most of our autocorrelation of frequency is centered near zero, right? Which comes from a narrower spectrum. Makes a lot of sense, doesn't it, right? A narrower spectrum is going to have most of its autocorrelation centered near zero. And likewise, in time domain, we have more triangular shaped pulses. We're going at narrower ridges in our autocorrelation function in time, which goes along this dimension. And then, of course, you can combine those two thoughts in your head to get the entire function. Now, when we look at the output, you can see that we have nice blue locations in between. It goes deeper. We saw those deeper nulls in the picture. I'm not sure that is actually not just due to calculation and the way the calculation was performed. For example, we're not using measurement noise here, so while you saw that the amplifier takes up the noise, it would take up signal and noise in real life. I'm not so sure it takes up noise in this case because of the fact that it was a simulation. So because you're centering these ambiguity functions on the optimum energy, you may actually appear to have lower nulls in your correlation. I think that's what's happening here. That's why you see these low blue points in the middle. But notwithstanding that idea, the red points are wider here in the time domain. So as we go out in time, we see that we have flatter autocorrelations, or wider range side lobes. And as we go in Doppler at a fixed time value, you can see that the darker colors extend farther out, which is a result of the spectral spreading, right? It's not a result. The spectral spreading and the widening of these Doppler contents are results of the same nonlinearity that's happening. So this really hits home. What do we do now as amplifier designers? And this is where we are. We've pretty much shown you what we're working on now. So can we use these techniques that Dr. Marks has talked about, look at this ambiguity function instead of this one? You know, we'll do the whack-a-mole here. We'll take this result and then run it back into the POCS optimization and optimize for spectral mass. This is amplifier in the loop optimization. Then the question is, can we optimize the amplifier to get the ambiguity function we want? Can we actually optimize the amplifier along with the waveform to get the ambiguity function, which is, unlike my graduate student who quickly learned that spectral spreading wasn't the only the goal, right? Here, our ultimate goal is detection. It's this picture. This is the ultimate goal of the radar. And we also want to make sure it meets spectral mask and efficiency requirements. And we want to optimize this amplifier as well as its waveform and hence the properties to get this. A lot of work's been done in the microwave community on pre-distortion. It's always done in view of the spectrum. But think about this, now we're optimizing a waveform to get an ambiguity property. Related, but not completely the same task. So, I guess in concluding this workshop, and then we've left intentionally a few minutes for discussion and ideas. We think you'll probably give us ideas as much as maybe we've given you some too, and we appreciate that. So we kind of started out, Larry really set us a stage for how tube and solid state radars cause significant issues in spectral spreading and how radar and communications are going to have to learn to work together and some of the related infrastructure challenges of making that happen. And we talked about linearization of power amplifiers. We need to do that. And we went over some linearity and efficiency techniques to accomplish that. We talked about real-time reconfigurable radar transmitters in both circuit and waveform using techniques such as the real-time circuit optimizations, real-time waveform optimizations, and the Smith tube to be able to accomplish these goals. To operate in a future-crowded, reconfigurable, and adaptive spectrum environment. So we're designing reconfigurable and adaptive systems for a reconfigurable and adaptive environment that we believe should and hopefully will become the spectrum environment of the future. And, you know, when I've been at conferences and I've been hearing these talks about millimeter wave, and I think millimeter wave is real. I think that it gives us a chance to extend the spectrum in one dimension, and I'm very happy to see that. But I think on the other hand, as Larry and I have been talking, we need to use the spectrum we have better, because there are some radar functions and probably some communication functions that will not operate in millimeter wave. They need certain frequencies, and so that lower end of the spectrum, we need to figure out how to use it better. We can't just keep designing for higher and higher frequency performance and allow that to excuse poor utilization of the spectrum we have. So we will have to design techniques to reallocate and be reconfigurable and adaptive to better use the spectrum we have, and that's what we're working on. And the goals are fast adjustment to meet the three goals: range, Doppler resolution, spectrum performance, and power efficiency as we see it, under the umbrella of communicated S-band system. So anyway, that's the workshop. Thank you, Bob and Larry, for your contribution.